I think audio and video is clear. Okay, so let's start the session. So this session is part 2 power system, and in this session I'm going to cover the per unit system and the load flow studies, and also I'll discuss a little bit of symmetrical fault. Okay, so we'll tackle these 3 topics in today's session. Try to complete it, because the time is not that much. I mean, the time is only for 2 hours. So I have to take class only for 2 hours, so that's why I have to go a little fast. But anyway, we'll try to cover all these topics. So let's start the session, guys. This is my introduction, and this series is Maha Marathon series, and this series has started from 3rd of January, in which we have completed almost every subject. Now we have started the core part. So power system is going on. After that, we'll take machine from tomorrow onwards. We have a session on machine, and then we'll take sessions on power electronics. Okay, so there is one more session which will be on 10th of January, and it will be taken by Dheeraj Sardana sir. And regarding this GATE 2024, how to ace GATE 2024. So if you have your juniors or maybe your friend who want to prepare for GATE 2024, you can recommend this session to them, and they will get the idea. Okay, and they will get the tips and tricks. For general aptitude, Rakesh Talleja sir is coming soon with his ideas on aptitude, and I hope that in general aptitude you can score 15 out of 15 after attending this class. Okay, so don't skip this class, it's important. For mathematics, again Ankit Joshi sir and Rakesh sir will take marathon session on mathematics. So it is again the date will be announced soon, and you can enjoy this session also, because mathematics is very important. It contains 15 marks approximately, so you have to score, and it's easy. The best part is it's easy. So better you attend this class and complete your mathematics part. It's time for the test series, guys. So start joining the test series. BYJU'S Exam Prep is also giving you the test series, so you can join this test series, and there will be so many benefits of this test series. Approximately 4,000 questions are there, and I mean the interface is exactly same which is provided by the GATE. Like scientific calculator and the idea, I mean the review type of questions or something like that. So everything is same. So you can join this test series, and you can check your speed and accuracy and your correction. You can improve your preparation. Okay. So before starting the session, please subscribe this channel if you haven't subscribed it, and like this session and press the bell icon so that you get the notification. Don't forget to like. Okay. Let's start the session, guys. I think it's time to say yes or no. How is the Josh? Tell me. Okay. Okay. Is it clear now? Tell me. Is it clear now? Okay. So there was a internet problem. There was a small glitch. Okay, now it's fine. Okay, thank you. So I think we should start now. So let's start the session, guys. Let's start the session. So first of all, let's discuss about per unit system, because per unit system is again very important, and maximum students are confused in per unit, especially whenever the per unit comes in 3-phase system. Okay, in single phase it's very simple, but in 3-phase it creates some problem. So we'll tackle those problems, and we'll try to understand it. What is the meaning of per unit? Per unit means with respect to something you are looking at the value. Okay, you have selected some base value. With respect to that base value, you are converting every quantity in per unit form. So the per unit value is actual value upon base value. It means you must know the base value. Once you get the base value, you can divide the actual value with the base value, and you can convert, you can calculate the per unit value of the quantity. Now in power system we have actually 4 quantities. What are those 4 quantities? Voltage, current, power, and impedance. We have actually 4 quantities. Out of these four quantities, if you know the base value of any two, out of these four quantities, if you know the base of any two, you can calculate the base value of the other two. Because base you have to select the base value. Then you can calculate the per unit value. Per unit system, it's kind of you can say it's a change of currency, you can say. The currency you can change, na? Wherever the amount is very high, then you don't take it in rupees, you don't call it in rupees, you call it in dollars. Okay, so actually per unit is similar to that. Per unit means you are changing the currency. So what you have done is you have to select the base value, and then using that base value you can calculate the per unit value. To calculate the base value, there are four quantities. Out of these four quantities, you can assume base of any two quantities. Once you get the base of any two quantities, other two quantities base you can easily calculate. Okay, so let's say I assume the voltage base value as VB and the current base value as IB. If you have selected the base value for voltage and current, then you can easily calculate the base value of the power, VB into IB in single phase case. Okay, in single phase case, VB into IB will be the power base value, and the impedance base value is VB upon IB. Okay, this way you can calculate the impedance base value. It's simple. But sometimes what we do is we don't select the base value of VB and IB. What we do is we select the base value of power and the base value of voltage. Generally, these two quantities are provided to you. So let's say we know the base value of voltage and the power. Now the current base value will be equal to S base upon V base. This way you can calculate the base value of the current, and the base value of the impedance will be Z base, and that will be equal to, tell me, because we know that the VB upon IB is the base value of the impedance. Now we know the I base value is this. So VB divided by I base, VB base value of the voltage, we know that it's VB, divided by the base value of the current is this. So what you can do is you can write it like this: VB upon SB upon VB. So it will be VB square divided by SB. This way you can calculate the impedance base value. Okay, so it's easy peasy. We can if you have any two base value of any two, let's say you have selected base value of these two quantities, with the help of these two quantities you can calculate the base value of the other two quantities like impedance and the current. So there is no problem at all. In single phase you can see that the base current is base power, let's not call it MVA. This will be the current base, and impedance base is base voltage upon base current. So base current is this, so you can put the value, so you'll get base voltage square divided by base power. Okay, divided by base power. Is it fine, guys? So this will be the formula for base impedance. Now let's say you know the per unit value at some base. Let's take a question. Let's say I have a question in which Z per unit is given to you. Let's say Z per unit is 0.5 at 400 volt and let's say 20 kVA. On this base, per unit value of the impedance is provided to you. Now I want to calculate Z per unit value at 500 volt and 10 kVA. At the new base, I want to find the Z per unit value. So what you can do is, it's again simple. You don't need to remember any formula. What you can do is, from this expression, you can calculate the actual value, because actual value will remain same. Only the per unit value will change, the base value will change. Okay. So in the first case, the base value is provided to you. Based on this base, you can calculate the Z base. What is the Z base, guys? Based on the voltage base and the power base, you can calculate the impedance base value. So the impedance base value will be equal to 400 into 400 divided by 20 into 10 raised to power 3. Fine. This way you can write the base value of the impedance. So it will be, okay, you can say that it's 8 ohm. So base value came out to be 8 ohm. Fine. Now this per unit value, we know that the per unit value is actual value divided by the base value. So 0.5 is equal to Z actual divided by Z base. Z base is 8. So from here Z actual will be equal to, the actual impedance value came out to be 4 ohm. Is it fine? This is the actual impedance value. This is the actual impedance value. So using this per unit value, we have calculated the actual impedance value. Fine. Now in the second case, we get the actual value. This actual value will remain same in the second case, because whatever the first case or the second case, per unit value will change, the base has changed, so the per unit value will change, but the actual value will remain same. So what we have done is, we have calculated the actual value using this expression. We have calculated the actual value using this relation. We know the base impedance, multiply with the per unit value, you'll get the actual value of the impedance. So actual value of the impedance came out to be 4 ohm. This 4 ohm is also valid for the second case. Now for the second case, can you calculate the Z base? For the second case, for this case, the base impedance will be 500 into 500 divided by 10,000, okay? So it will be 25 ohm. So for the next case, for this case, base is this 25 ohm and the actual value is 4 ohm. So Z per unit, the new Z per unit you can calculate, is Z actual divided by the new base, that is 25. Okay, this is the answer now. Is it fine, guys? So 8 divided by 25, this way you can calculate the new per unit value of the impedance. Now if you know the direct formula, you can put the direct formula also. The direct formula is Z per unit new is equal to Z per unit old value is this, into V base old upon V base new, take square of it, into S base new divided by S base old. Okay, you can also remember this formula, and using this formula you can, this formula is not different. This formula came from this concept only. If you know the Z per unit old, what you can do is, if you know the Z per unit old, multiply it with Z base old, multiply it with Z base old, and Z base old is V base old square of that divided by S base old. Okay, you just multiply it with the Z base old so that you get the actual value. So this is the actual impedance. Now what you can do is, you can divide it with Z base new. This is the actual value. We have multiplied Z per unit old with the old Z, V base new with the Z base new. You will get the Z per unit new. Okay, Z per unit new. So if you understand this concept now, the same I have using the same concept I have designed this formula. Okay, so you can remember this formula, and directly using this formula you can calculate the value of Z per unit new. I hope it is clear to everyone. Is it fine, guys? Okay, let me repeat this again. I told you that you don't need to remember this formula, from where this formula derived. That's why I'm telling you, you know the Z per unit old. So what you can do is, if you can multiply this Z per unit old with the Z base old, if you multiply this Z per unit old with the Z base old, you'll get the Z actual. This is my Z actual. Z actual divided by Z base new. This is the Z base new, 1 upon Z base new. S base is in the denominator. So Z actual divided by the Z base new will be the Z per unit new. So I have simplified this, and you get this formula. So you don't need to remember this formula if you know the concept. Actually, in both the cases, the actual value will remain same. Only the base value is changing. Okay, I hope you understood it. So if you remember this formula, then you will be little fast. You can solve it little fast, because then you have to put the values only, and then you can directly solve it. Okay, so this way you can convert the old Z per unit into new Z per unit. On the new base, you can convert the calculate the Z per unit value. Okay, now let's proceed with the next topic. Why I study per unit value? What's the advantage of having? What's the advantage of getting per unit value? Okay, let me tell you what's the advantage. What's the advantage of that much important? The first, the internet is creating problem, guys. Okay, so sorry from this side, but anyway, so what's the advantage of knowing per unit value? A minute, again it's buffering. I don't know why it is happening. Okay, guys, just give me 1 minute. Let me see. Actually the internet speed is fluctuating, that's why it's buffering. Okay, so anyway, let's come again. So I told you what is the advantage, why I'm studying, why I'm teaching you per unit system, the large values of the quantity. So I have to convert them in lower unit. Okay, I have to make. Is it clear, guys? Tell me. Is it clear? So there is some internet fluctuation, and there is some internet fluctuation, guys. Let me see. I think it's fine now. Is it fine? Please tell me. Is it fine? Okay, okay, thank you. So just give me 1 minute. Okay, so I was telling you why we are using this per unit system. The per and these quantity have very large amplitude. Now what we need to do is we need to minimize. We can't handle the large quantities. That's why we have to make the amplitude small. To make the amplitude small, we need the per unit system. Okay, that's why we are studying per unit system. Now there is one more advantage of knowing per unit system. What is that advantage is, let's take a transformer, a single phase transformer. Let's say I have a single phase transformer, and let's say I have a circuit like this. Let's say I have a circuit like this. Let's say this is the circuit I have, and here you have some reactance. Okay, and let's say this is 1:10, 1:5, and this is 2:5. Okay, this is the transformer, and the rating of the transformer maybe 100 kilovolt to 500 kilovolt. Okay, 100 kilovolt to 500 kilovolt, and the power rating is 200 MVA. Okay, this is J9 ohm, this is J6 ohm. Okay, and this is J36 ohm. Fine, and here you have the load terminal. Here you have the load terminal. Okay, this is the circuit which is provided to you. Flow. This is my receiving end, sending end. This is my sending end. Okay, at this end the voltage is, let's say, at this end the voltage is maybe you can say 500 on this side, let's say, and if it is 500, then it will be maybe let's call it 10 kilovolt. This is 10 kilovolt. Okay, on this side you have the voltage of 10 kilovolt, and the sending end voltage is not 10. Wait a minute. Let's say that this voltage is maybe 50 kilovolt, or let's say 500 kilovolt is this. This is my 500 kilovolt, and on this side the voltage is let's take 100, maybe 1000 kilovolt. Okay, on this side you have 1000 kilovolt, on this side you have 500 kilovolt, and I need to calculate how much power is getting transferred via this transformer. And let's say the angle of this is 30 degree and angle of this is 0 degree. It is also provided to you. Angle of this voltage is 0 degree and the angle of this voltage is 30 degree. The sending end voltage is at 30 degree and the receiving end voltage is at 0 degree. I need to calculate how much power will be transferred from the sending end to the receiving end. Now how to calculate that? We can calculate this power flow using per unit system, because otherwise it will be very difficult. Otherwise it will be very difficult to handle this situation, because we need to bypass the transformer. Now how to bypass the transformer? We don't want to use the transformers. Now how to use, how can we avoid the transformer? Using per unit system. Using per unit system you can bypass the transformer. How? Let me tell you. Let's say you have a single phase down. Let's take a simple case. Let's first take a simple case. Let's say I have a simple transformer, 100 is to 500 volt, okay? And let's say here the resistance is of 100 ohm, okay? And the resistance is of 100 ohm and this transformer is 20 kVA transformer. Now, what I want to do is, I want to look at the resistance on this side. Can you calculate the resistance from this side? We have a transformer, the transformer is 1:5 ratio, and I want to calculate the resistance seen from between these two terminals. What is the resistance seen between these two terminals? Can you calculate, guys? This resistance will be 100 into 1/5 square, okay? So it will be equal to 4 ohm. So the resistance seen from the low voltage side is 4 ohm, fine? Resistance seen from the low voltage side is 4 ohm. Now what we can do is we can calculate the per unit value of this voltage, per unit value of this resistance, and also the per unit value of this referred resistance. How to calculate the per unit value? How to calculate the per unit value? In case of transformer, remember one point. In case of transformer, remember one point. If you know the base value on this side, you can easily calculate the base value on the other side. How to calculate the base value on both the sides? So what I need to do is I need to select the base. So let's say on the low voltage side, I select the base voltage as 100 volt and base power as 20 kVA. So in case of transformer, just remember one point. Whenever you go from primary to secondary, the base voltage or the base current will change according to the turn ratio, but the base power will not change. It means on this side, the base voltage will be 100 will become 500. So the base voltage will become 500 on this side and the power base will become 20 kVA. Is it fine, guys? So we can calculate the base value like this. If you know the base value on one side of the transformer, let's say the voltage and the power base you know, then you can calculate the base value of the voltage and the power on the other side, on the high voltage side. How can you calculate that? Let's say on this side the base value is 100 volt and 20 kVA is the power base. Now you can refer this voltage on this side, so it will become 500, we know that. So the base value will change to 500 volt for the voltage, and the power base will remain same because transformer does not change the power value. That's why the power value will remain same, the power base will remain same. Now if you want to calculate the Z base on this side and Z base on this side, what is that Z base? So Z base will be equal to V base square, which is 100 into 100 divided by 20 kVA, 20 into 1000, fine? Now you can calculate, you can cancel this. So Z base came out to be 1/2 ohm. On the low voltage side, Z base is 1/2 ohm. And on the high voltage side, the Z base is 500 into 500 divided by 20 into 10 is to power 3, okay? So this 4 power will be cancelled. So it will be 25/2. 25/2. Is it fine, guys? So on this high voltage side, the Z base is 25/2. On the low voltage side, the Z base is half. So what we can do is we can calculate the per unit value of the impedance. What is the per unit value of this impedance? Tell me. Actually, it is 100 ohm. And the base value is 25/2. So if you want to calculate the RL per unit value on the high voltage side, so it will be actual value divided by the base value on this side. Base value of the impedance on this side is 25/2, okay? So 25/2. So it will become 8 ohm. It will become 8 and per unit value is unitless. So the RL per unit on this side is 8 per unit. If you refer this resistance on this side, the resistance value will become 4 ohm. Now I want to convert this 4 ohm in per unit on low voltage side, because from the low voltage side you can see that the resistance in will be 4 ohm. From the low voltage side, if the resistance in is 4 ohm, now what is the per unit value of this 4 ohm? So the per unit value will be RL per unit on low voltage side will be the actual value 4 divided by the base value, which is half. So it came out to be 8 again. Now what does it mean? What does it mean? It means that the per unit value of the resistance, whether you look at the per unit value on this side or you refer this resistance on this side and then calculate the per unit value, it will remain same. per unit value does not change in transformer. Whether you look on the high voltage side or on the low voltage side, it doesn't matter. Per unit value of the resistance will remain same. Fine. What else will remain same? Voltage per unit value. If you look at the voltage per unit value, let's say actual value here is 100 volt. If you apply 100 volt here, it will become 500 volt here. So if you calculate the per unit value of the voltage, 100 divided by the base value 100. So on this side voltage per unit is 1, and on this side actual value is 500 now, and the base value is 500 again. So voltage base will also remain same. Across these coil voltage per unit value will also remain same, and the current per unit value will also remain same. So in transformer, just remember impedance per unit value and the voltage per unit value and the current per unit value, they will remain same whether you are looking on the primary side or the secondary side. It means if you want to draw the diagram in per unit, if you draw the equivalent diagram of this situation in per unit, it will be simply this diagram. It will be simply this diagram. This is 8 per unit and the voltage across it is 1 per unit. You don't need to show the transformer. The transformer has bypassed. If you are using the per unit value, you don't need to show the transformer, okay? Transformer has bypassed. This is the beauty of the per unit system. It means you can bypass the transformer if you know the per unit value of the impedances. The per unit value of the impedances will remain same on both on primary and secondary. So there is no meaning of primary and secondary now. In per unit situation, there is no meaning of primary and secondary. So what you can do is, you can bypass the transformer if you use the per unit value. Is it fine? If you use the per unit value, you can bypass the transformer. Now look, this is the situation we have, and we need to calculate the power flow at the active power at the receiving end. How much active power will be received at the receiving end? We need to calculate that. Now how to calculate it? It's very simple. What you need to do is, you need to bypass these transformer. You need to bypass these transformer. How to bypass these transformer? What you can do is, first to write these impedances value in per unit value. Okay? If somehow you can write these impedance value in per unit value, then you can bypass. Now how to calculate them in per unit value? Let's select some base. So I select base value on this side. So I start from this side. On this side, let's say the base voltage is 100 kV. I select the base voltage as 100 kV. Okay, and the base power as 200 MVA. On this side, if the base voltage is this, what is the base voltage on this side? Since the transformer is 1:5, the base voltage on this side will become 500 kV and the power base is 200 MVA. I have selected some base, na? Base you can select by your own. Okay, it's not necessary that they will provide you the base. Base you can select your own. Okay, you can take your own base. So what I have done is, I have selected the base as 100 kV on this side and 200 MVA on this side. So this is the voltage base and this is the power base on the low voltage side of this transformer. So on the high voltage side of the transformer, the voltage base value will change to 500 kV and the power base will remain same. Now let's come to this side. On this side, the voltage will be, now tell me the voltage base value on this side, 500 into 5 by 2. Okay, 500 into 5 by 2. It means 500 into 2.5. So it will become 1250 kV. Please check it. 1250 kV. I suppose this is correct. So this is the voltage base value and the power base value will remain same. 200 MVA. Is it fine? So we have calculated the base voltage and base power on every side of the transformer. On every side of the transformer, we have calculated the base value. Once you know the base value on this side, you can easily write the base value on this side and you can easily write the base value on this side. Power base value will remain same and the voltage base value will change according to the turn ratio. Okay, just remember it. Now what we can do is, we can calculate the impedance base value also. Now if you want to calculate the impedance base value on this side, what is the impedance base value on this side? Tell me guys. It will be 100 into 10 to the power 3. Take the square of it, divided by 200 into 10 to the power 6. 200 into 10 to the power 6. Is it fine? So this 10 to the power 6 will cancel and here you will get 100 into 100 divided by 200. Okay. So it will be 50 ohm. So you can see that on this side, the base impedance is 50 ohm. Base impedance is 50 ohm. Now what about this side? On this side, the base impedance is 500 into 500 into 10 to the power 6 divided by 200 MVA. 200 into 10 to the power 6. Okay. So this is cancel. This 20 cancel, and then it will become 2500 upon 2. So it will be 1250 ohm. Is it fine, guys? Tell me, everyone. So this resistance came out to be, on this side the Z base came out to be, on this side the Z base impedance came out to be, tell me guys, what is the base impedance? Base impedance came out to be 1250 ohm. This is 1250 ohm. Is it clear, guys? Tell me. 500 into 500 into 10 to the power 6 divided by 200 into 10 to the power 6. 10 to the power 6 will cancel, and then 20 will be cancelled, and 2500 upon 2. So you can say that 1250 ohm will be the base impedance on this side. Now, what is the base impedance on this side? We don't require the base impedance on this side because there is no impedance connected here. Now what we can do is, we can calculate the per unit value of this system. Now what is the per unit value of this voltage source, first of all? So let me draw the per unit diagram. What is the value of this source? This source actual value is 1000 kV and the base value is 100 kV. So the per unit value on this side is 10 angle 30. Is it fine? This is the per unit value of this voltage source. We have divided this voltage with the base value. Okay, so it will be 10 angle 30. Now what about the impedance per unit value? The impedance per unit value came out to be, tell me the impedance per unit value. Impedance per unit value came out to be J36 upon 50. So it will be J36 upon 50. Fine. Now there is no need to show this transformer. Transformer is bypassed. If you are writing everything in per unit, there is no need to show the transformer. Okay, transformer will get bypassed. Now come to this side. On this side, what is the per unit value of this impedance? The per unit value of this impedance is J9 divided by 1250. Similarly, the per unit value of this impedance is J6 divided by 1250. Is it fine, guys? Fine. Now you bypass this transformer again, and here you have the load. We don't know this load, but we know the voltage across the load. So voltage across the load is 500 kV. Now tell me the base value of the voltage. Base value of the voltage is 1250 kV. So we can convert this in per unit. In per unit, this voltage will be equal to 500 divided by 1250. Okay, so this will be cancelled, and here you will have 10, and here you have 25. So again 2 by 5. Okay, so this will be 2 by 5 per unit. Is it fine, guys? So this voltage came out to be 2 by 5 at an angle of 0. So we have calculated per unit value of this voltage and the per unit value of this voltage and the per unit value of the impedances, and there is no need to show the transformer. This is the beauty of the per unit system. This is the beauty of the per unit system. Now what you can do is, now you know this receiving end voltage. Let's assume this as ground. This is the sending end voltage, this is the receiving end voltage, and there is a reactance in between the sending end and this receiving. There is no need for this, na? Active power. Active power will flow from this side to this side, from source to load. Okay, how much power will flow? We know that there is no resistance, so as my VT terminal voltage in per unit, it's 2 by 5 angle 0, and this per unit is 10. So what you can do is 2 by 5 is 0.4. 0.4 into 10 divided by the per unit value of the reactance. This is the reactance. This is the series reactance which will come into picture, because at this point you have the VT and this point we have the EF. So this is the series reactance which will come into picture. So what we can do is, we can calculate the resultant X. You can put the resultant X here. What is the resultant X, guys? If you can calculate the resultant X, let me calculate it. Let me calculate for you. Let me have calculator, because I don't. Let me check whether I have the calculator. Yes, I have the calculator. So I can calculate this value. Okay, I can calculate this value. If you want to calculate this value, this value came out to be 36 divided by 50 plus, it came out to be 0.7272. Okay, it came out to be 0.7272. This is my X. Is it fine, guys? So I have EF VT by XS sine delta, sine 30. This is the active power in per unit which will be delivered to this load. Okay, this is the active power. Okay, I don't know what's the issue. Yeah, tell me guys, is it clear? Everyone, is it clear? Is it clear now? Okay, still buffering? Is it still buffering? I think it's clear now. Okay, so what I was telling you that once you convert everything in per unit, now you don't need to show the transformer. You can write their per unit values. So the circuit is this. Now you don't need to show the transformer. Okay, now you don't need the voltage. I have calculated these voltage in per unit, this voltage also in per unit. Now you have this voltage at the sending end voltage and this voltage at the receiving end voltage. So on this reactance, you can see that whatever active power will go through these reactants, the same active power will go here, because this reactance will not take any active power. Fine. Now how to calculate the active power flow? How much active power will flow? Okay, tell me how much active power will flow via this. So you know this supply voltage 10, the magnitude is 10, and the voltage at the load end is 2/5 per unit. 2/5 is 0.4, divide by this reactance. I have added this reactance. If you want to add this reactance, it will be 0.7272. Sine of angle between them, this is 0, this is delta, so the angle between them is 30 degrees. So sine 30 I have written. Okay, this is my sine 30. So this much of active power will be received at the receiving end. Now the question is, this power is in per unit. This is not the actual power. Now how to calculate the actual power? First you need to calculate the per unit value of the power, multiply by the base value of the power on this side. Okay, so the base value of the power is 200 MVA. So what you can do is, you can calculate this value. Let me calculate it for you. So it will be 0.4 into 10 into 0.5, sine 30 is 0.5, divide by 0.7272. Okay, so if you calculate it, you will get 2.75. So it will be 2.75. 2.75. Is it correct, guys? 2.75 per unit power will received here. Now the actual power will be the base power multiplied by 2.75. So base power is 200. So what you can do is, you can multiply with 200. Okay, the per unit value you can multiply with 200. So the answer came out to be 550. Answer came out to be 550.0 megawatt. Okay, this will be the active power which will be received at the receiving end. So this way you can calculate, you can use the per unit system to calculate this power. So I think calculation is correct. Please check the calculation, because I don't sure about the calculation, but I have told you the method why I'm using the per unit value. Okay, why I'm using the per unit? Because in per unit you can bypass the transformer. You can handle the large values. Large value can be minimized. Okay, that's why I'm going towards per unit. And I told you how to handle the transformer. In case of the transformer, the per unit value on this side of the voltage and the per unit value of the voltage on this side, they will remain same. Similarly, the per unit value of the current on this side and the per unit value of the current on this side, they will also remain same. The per unit value of the impedance will also remain same. If you want to draw the equivalent diagram of this transformer in per unit, you can show it like this. This is the equivalent diagram of the transformer in per unit. So it means in per unit system, you don't need to show the transformer. Transformer can be bypassed. Okay, I hope it is clear to everyone. Now there is one question. There is one more question I have. And if you look at this question, the circuit shown below, there are three parts of one phase system, of single phase system, and connected with two transformers. So there are actually two transformers, transformer AB and transformer BC. Transformer AB is 1:10 and transformer B is 2:1. And now this side is A, this side B, this side C. There are three parts of the circuit system, and in this system there are two transformer. One is 1:10 and other one is 2:1, and the load is 300 ohm. Fine. What I need to do is, it is given that the rating of the transformer AB, is 10 MVA, 138 to 13.8 kV. It means on this side, okay, the leakage reactance is 10%. Let me check the original file, because I think he has done some mistake in typing the question. Let me check the original file so that I can rectify this question and I can correct the statement, because I don't think that this statement is correct. Wait a minute, guys. I think okay, so this is 10 MVA, 138 to 13.8 kV, and the leakage reactance is 10%. It means the reactance of this is given as 0.1 per unit. Okay, at its own base, the reactance of the transformer is given as 0.10. Okay, this is the leakage reactance. Now for transformer B, again it is 10 MVA, 138 to 69 kV, leakage reactance is 8%. Fine. If the bus in circuit B is selected as 10 MVA 138 kV, in this B region, the base is selected as, it is not bus, it is the base. If the base in the circuit B is selected as 10 MVA, so the base on this region is given to you, 10 MVA and 138 kV. This is the base which is provided to you in this region. So base is provided in B region. Now what I need to do is the per unit value of 300 ohm on the circuit A side. I need to calculate the per unit value of this 300 ohm on this side. On this side of the circuit. How to calculate the per unit value of 300 ohm on this side of the circuit? Tell me, guys. Now what we can do is, first of all, we will define the per unit, the base value. We will define the base value. On the circuit B side, this is the base we have. This is the power base and this is the voltage base. So what we can do is, we can define the base on this side also and on this side also. Because you know the base value of the circuit in this B region. Now what is the base value of power and voltage in this region? Tell me, guys. This transformer is of 138 to 10. So on this is high voltage side, let's call, and this is low voltage side, because 138 to 13.8 is this. It means this side is the secondary side and this side will be the primary side. So on this side, the voltage base value is 13.8 kV and the power base value will remain same, 10 MVA. The power base value on this side, the power base value is 10 MVA. On this side also, the power base value will remain as 10 MVA. Now let's come to this side of the transformer. On this side of the transformer, the power base value will remain same as 10 MVA. What about the voltage base value? If you look at the voltage base value, it is 138 to 69. So it means this side is 138, so this side will be 69 kV. So I have calculated the base value in this region, in this region, in this region. This region base value was provided. Based on this, I have calculated this region base value and this region base value. Now you can convert this 300 ohm in per unit value. Now tell me the per unit value. First of all, you have to calculate Z base on this side. Z base on this side is 69 into 69 into 10 is to power 6 divided by the power base, that is 10 into 10 is to power 6. Is it fine? So I have calculated it will be 69 into 69 by 10. Okay, this is my Z base. Now I need to convert this in per unit. How to convert this in per unit? Actual value divided by the base value. So the actual value is 300 divided by the base value. Base value is 69 square and into 10. Is it fine, guys? This way you can convert, you can calculate the per unit value of this impedance. What is the per unit value of this impedance? Let me calculate it. So it will be 3000 divided by 69 square. It came out to be 0.63. It came out to be 0.63 per unit. So the per unit value of this impedance, came out to be 0.63 per unit. It means if you are looking this resistance on this side, per unit value will remain same. If you are referring this resistance on this side, per unit value will remain same. Why? Because you can bypass these transformer. You can bypass these transformers. So per unit value will remain same. It doesn't matter on which side you are looking the resistance. Okay. So per unit value will remain same, and the answer came out to be 0.63 per unit. So the answer for this is the per unit value of 300 ohm on the circuit A side will again remain same, 0.63 per unit, because per unit value will not change. Now let's come to the next case. In the next situation, find the voltage regulation if the voltage at the load is 66 kV. It means at the load terminal, the voltage is provided to us, and this voltage is 66 kV with assumption that the voltage input to the circuit A remains constant. It is given that the voltage at the circuit A at this terminal, the voltage remains constant. Now how to calculate the voltage regulation? It's again very simple. What you need to do is, you need to draw the diagram in per unit. Let's bypass these transformer. if you can bypass these transformer, then this transformer can be replaced with its leakage reactance. We know the leakage reactance of this transformer. What is the leakage reactance? The leakage reactance is 0.10 per unit, J.10. But the problem is this per unit value is on this base, and the base we have selected is again the same. If you are looking at the base value on the high voltage side, the base value is 138 kV 10 MVA, and the transformer is also at 138 kV 10 MVA. It means this per unit value is given on this base, and we are also selecting the same base. So the per unit value will remain same. Otherwise, we have to convert this per unit value in the new base. Convert this per unit value in the new base. But the base on which this per unit value is provided to us is same as the base we have selected. Whether you take on high voltage or on low voltage, no problem. If you're looking on the low voltage side, the transformer rating is 10 MVA and 13.8 kV, and on this base the leakage reactance is this. Now on the low voltage side we have selected same base value. That's why this leakage reactance will remain same. Okay, so I don't need to convert it on some new base, because the old base and the new base is same. So the per unit value of this transformer is J.10. So you have to show the transformer like this. So this transformer can be represented by its leakage reactance like this. Now, what is the leakage reactance of this transformer? And I know that the transformer has to bypass, because I am writing in per unit value. Now, let's come to the transformer number 2. For the transformer number 2, the leakage reactance is J0.08 per unit. Now, on which base this leakage reactance is provided? Tell me, guys. On this base, the leakage reactance is provided. If you are looking on the high voltage side, it's 138 kV and 10 MVA. And on high voltage side, the base we have selected is same. And on this base, this reactance is provided to you. And this is the same base that we have selected. So it means the per unit value will remain same. The old base and the new base remain same. Okay, so the per unit value will also remain same, 0. So the per unit value will be 66/69 at an angle of 0 degree. Is it fine? This is the per unit voltage. Now let's calculate this value. 66/69. It came out to be 0.96. You can say this voltage is 0.96 at an angle of 0 degree. This much of per unit voltage is the voltage across the load terminal. Now you can calculate the load current IL. What is the load current IL, guys? IL came out to be 0.96 at an angle of 0 divided by the impedance 0.63. Okay, we have calculated the line current. Once you get this line current, what you can do is you can calculate this voltage. You can calculate this voltage in per unit. How to calculate? You can apply the KVL. So if you apply the KVL, this voltage Vs will be equal to 0.96 at an angle of 0 plus this drop J 0.18 into the current value 0.96 at an angle of 0 divided by 0.63. Okay, so we have calculated this voltage 0.96 angle 0 plus this drop. Okay, we have calculated this supply voltage Vs. Now what is this Vs? Let me calculate this. So this came out to be 0.18 at an angle 90 multiply by this factor 0.96 angle 0 divided by 0.63. Okay, and if you calculate this, it came out to be 0.995, 0.995, and there is some angle as 16 degree. Okay, so we have calculated this voltage 0.995 angle 16 degree per unit. So we have calculated this voltage and we know this voltage. Now we can apply the voltage regulation. So voltage regulation is, tell me guys, no load voltage magnitude. If there is no load, this voltage will appear here. So the no load magnitude is 0.995 minus the load voltage. Load voltage is 0.96 divided by the load voltage 0.96. Okay, this will be the regulation. If you want to calculate the percentage voltage regulation, just multiply with 100. You will get the percentage voltage regulation. Is it fine, guys? Tell me. I think it is clear to everyone. Now look at this question. This question was again very difficult to solve. because we need to calculate the voltage regulation. So we need to calculate no load voltage here, and then so what I have done is I have bypassed this transformer. There is no need for the transformer. Okay. And how to bypass the transformer? Tell me guys, how to bypass the transformer? There is only one way to bypass the transformer, using per unit. I have converted everything in per unit. This resistance in per unit, this voltage in per unit, this these reactances in per unit, and I have shown the transformer with their reactances. I have shown the transformer with their reactances. Okay. So this way you can draw the diagram and you can apply the KVL and you can solve it. I hope it is clear to everyone. Now let's come to three-phase system. So this was about single phase. Per unit in single phase is very simple. Okay. Per unit in single phase is very simple. You don't need to worry about these formulas, or maybe everything is simple. But in three-phase circuit, many things will change. In three-phase circuit, you have to be more careful about while calculating the per unit value, because in three-phase case, let's say you have a star connected system. Don't look at these formulas. Okay. Let's say you have star connected system. You have star connected system, and let's say they have provided you the base value. They have provided you the base value. So voltage base value for three-phase system is provided to you, and let's say power base value for three-phase system is provided to you. Now, what is the meaning of this three-phase base voltage? It means it is the line voltage. Remember, it is the base voltage of the line voltage. Base value of the line voltage. Remember, base value of the line voltage. Okay. This is the base voltage of the line voltage. Base value of the line voltage. And this is the base power of three phase. This is the base power of the three phase. Base power of three phase. Now, let's say you want to calculate the base current. Base current. What is the base current value? How to calculate the base current? The base current can be calculated. We know that this three-phase power is √3 VLIL. VLIL. This is the power S in three phase. Now, if you know the base value of this power and you know the base value of this line current, line voltage, then you can calculate the base value of this line current, IL base. So how to calculate the base value of the line current? That will be S three phase divided by √3 into V line base. Whatever the base value of the line voltage, you can calculate that, multiply by √3, and in the numerator you have three phase base power. So three phase base power divided by √3 VL base, you will get the IL base. So current base value you can easily calculate. The base value of the line current you can easily calculate. Okay. Now let's come to the Z base. How to calculate the Z base? How to calculate the Z base value in three phase circuit? How to calculate the Z base value? Don't look at these formulas. Okay, just avoid it. Remember these concepts of what I'm telling you. So the base voltage in three phase is provided to you. What is the meaning of the base voltage in three phase? It is the base voltage of line voltage, remember. And this is a three phase power. So what you can do is, you can calculate the line base current. This is the line base, because we know that the power is equal, three phase power is VLIL, √3 VLIL. So this is the line current. So we can calculate the base value of the line current like this. Okay. In star system, the line current and the phase current will remain same. So the base value of the phase current will also be the same. This is the base value of the phase current. Okay. Now let's come to the Z base. Z base is again very important. How to calculate Z base? Z base should be per phase, remember, because this is connected in star. So in star system, Z base should be per phase Z base. Now how to calculate Z base? We know that the Z base formula for per phase, if you are looking at the single phase only, so it should be V base single phase square divided by S base single phase, because we are looking at the single phase system. We are looking at the single phase, because Z base, this impedance is per phase impedance. So we have to calculate the Z base for single phase. Now how to calculate Z base? We have already seen in single phase case, this is the formula for Z base. Now the problem is, we don't know the single phase base value. Actually we know it. We know the base value of the line voltage. Now if you know the line voltage base value, then what is the phase voltage base value? Phase voltage base value will be V base three phase divided by √3. Is it fine, guys? and take the square of it. This is the phase, this is the base value of the phase voltage, and take the square of it. Divide by the base value of the power per phase. Base value of the power per phase. This is the base value of the power for 3 phase. You divide it with 3. Okay. S base 3 phase divided with 3, you will get the power base value for per phase system. Okay. So I have calculated the base power for per phase, and I have calculated the base voltage for single phase. Okay. And then I have used this single phase formula to calculate the Z base value. So if you calculate the Z base value, the Z base will came out to be, you can see that V base 3 phase square divided by S base 3 phase. Is it fine, guys? This is the formula for Z base, and the Z base is applicable for single phase situation. This is the base value of the impedance for per phase case. Okay, remember. So I have calculated the impedance base value, and please be careful how I have calculated this, because we know that the impedance is connected in single phase, in single phase, in this phase the impedance is connected. So Z base has to be this base value of the single phase impedance. So the single phase impedance base value can be represented like this, and I have put the value of V base single phase and S base single phase like this. So we have calculated like this. Now many students will say, sir, what's the difference? It is same as the single phase Z base. In case of single phase Z base, you have applied the same formula. In case of 3 phase Z base, you have applied the same formula. Actually, the result came out to be the same, but the process is different. The understanding is different. In 3 phase, remember, while calculating the Z base, then this Z base has to be per phase Z base. This Z base has to be per phase Z base. So be careful about this, guys. Okay, so please be careful, because this is important. So don't make any mistake. Okay, now let's proceed. Let me tell you one more point, and that point is, what is the per unit value in star delta conversion? Let's see how to calculate the per unit in per unit. If let's say some star values are given, what are the resistance per unit value in delta case? Let's try to take it. Let's try to solve it. Let's say I have a resistance value, and the resistance values are given as, let's say this is maybe 9 ohm, this is also 9 ohm, and this is also 9 ohm. Okay, in a 3-phase system, resistance values are given to you, and let's say the voltage, line voltage is 100 kV, and the power base value is given as maybe 200 MVA. Okay, 200 MVA. Let's take it like this, and better you call the resistances as 90 ohm. It will be more suitable. I mean, it's easy to solve. Okay, now I have taken these resistance values, and let's say the line voltage is this value, and the power base value is this. Now this point is A, this point is, let's say, B, and this point is C. Now what I want to do is, on the same system, everything is same, I want to convert this star in delta. Okay, if I convert this star in delta, the circuit will look like this. Is it fine? And this point will be A, this point will be B, and this point will be C. Now what is this resistance value? Can you calculate this resistance value? Yes, we can calculate it. That will be 90 plus 90 plus 90 into 90 by 90. So it will be 270 ohm, and this will be 270 ohm, and this will be 270 ohm. Okay, now you can see that I have converted this star into delta. So these values has changed. Now what I want to do is, I want to convert these I want to write these resistances value in per unit. Here also I want to write these resistance value in per unit. Now how to write the per unit value? Obviously I have to divide with Z base. I have to divide them with Z base. Okay, now how to calculate the Z base? I told you, in 3-phase system, Z base has to be per phase Z base. I have to calculate Z base, the single phase Z base I have to calculate. Okay. Now how to calculate the Z base? The Z base has to be V base single phase square divided by S base single phase. Okay. V base single phase square and S base single phase, because we are looking Z base per phase, no? Per phase we are looking. So what is single phase voltage? What is single phase base voltage? Three phase base voltage is given like this. So the single phase base voltage will be 100 into 10 is to power 3 divided by root 3. Okay. You take the square of it. You take the square of it. Divide by the single phase power base. Three phase base power is given to you. So single phase base power is 200 into 10 is to power 6 divided by 3. So this is my Z base in case of star system. In case of star system, okay, Z base in case of star system. Okay, Z base, per phase Z base in star system. Now what is this? This 3 will cancel, because here you have to take root 3 square, which is 3. Here you have 3. This 10 is to the power 3 is cancelled. So now it will be equal to 100 into 100 divided by 200. Fine. So this is cancelled and you'll get 50 ohm. So you can see that the Z base in star system came out to be 50 ohm. Okay. Now you can convert this 90 in per unit. If you convert this 90 in per unit, what is the value, guys? This value will be 90 by 50. 90. This will also be 90 by 50. So 90 by 50 is 9 by 5. It will be 1.8. 1.8 per unit. Is it fine, guys? So this resistance came out to be 1.8 per unit. This will also be 1.8 per unit. And this will also be 1.8 per unit. So we have converted them in per unit. I hope you understood it, how I have converted this. Okay. Don't look at the delta first. Look at the star first. So in star, we have calculated the Z base across this resistance. Since this is a single phase, so we have to calculate single phase Z base. Okay, I have calculated the Z base per phase. So this is the Z base per phase, and then I have divided this 90 with Z base per phase, and the per unit value came out to be 1.8. Now let's come to delta. In delta, I need to calculate Z base per phase. Again, this Z base I need to calculate. So Z base delta. Now what is this? Again, I need to take V base per phase square divided by S base per phase. Okay. Now what is the V base per phase? In delta, the line voltage will remain as the phase voltage. So it means this single phase voltage, this you can say this per phase voltage, the voltage across this, the base voltage value of the voltage, base value of the voltage came out to be 100 itself. Is it fine, guys? Tell me, have you understood it? Tell me, everyone. Per phase voltage across this impedance, what is the voltage base value? Voltage base value is 100 kV. 100 kV itself. It's not 100 by root 3 this time, because in star the phase voltage has to be 100 by root 3, but in delta the voltage across per phase is same as the line voltage. Okay, that's why the single phase voltage, I mean, if you are looking at only on this phase, this is the base voltage. Now what is the base power? Base power I have to divide it with root 2 with 3, so 200 by 3 into 10 is to power 6. Is it fine? Now you can see that this 6 is cancelled and you will get 3 into 100 into 100 divided by 200. Okay, so 20 cancel, this will be 50 here, so it will become 150 ohm. Now you can see that the Z base in delta is 150 ohm. Now calculate the per unit value of this impedance. So per unit value, Z per unit. So Z per unit will be equal to, or R per unit you can say, 270 divided by 150. Is it fine? This is cancelled. Now you can cancel with 3. So it will be 9 by 5. And 9 by 5 came out to be 1.8 again. Okay. So you can see that the per unit value is 1.8 per unit again. So what you can conclude? What can you conclude? Tell me, guys. Now you can conclude that the per unit value in star and in delta remains same. The per unit value will remain same. You can see that. This is the final conclusion. So please be careful about this. Per unit value in star and in delta remains same. I hope it is clear to everyone. Okay. So if let's say this resistance is given as 1.2 per unit, and this is again 1.2 per unit, and this is again 1.2 per unit, and you want to convert this in delta. If you want to convert this star in delta, the value will remain same. 1.2 per unit here, 1.2 per unit here, and 1.2 per unit here. Is it fine, guys? Please remember this. I hope it is clear to everyone. Tell me, everyone, is it clear? Now what I can do is, now I can go with the star delta current and voltage case. Now let's look at the current and the voltage case. Okay, be careful this time. This is again very important. This is very important. So you have to be more careful about this current and voltage, because this is the more, this is the crucial point, and maximum student do the mistake in this point. What I am going to tell you. What is the current relation in per unit in star and delta? Let's say you have the sources in star. Let's say you have the sources in star. Okay, let's say you have the sources in star. Okay, now let's call it N. This point is A, this point is B, and this point is C. Let me ask you. Let's say this voltage is 1 angle 0 per unit. This voltage is 1 angle minus 120 per unit, and this voltage is 1 angle plus 120 per unit. Okay, I have written these voltages in per unit. Okay, I have written these voltages in per unit, minus 120 in per unit. Okay, and this is 1 angle 0 per unit, 1 angle 120 per unit. Now what I want to solve, what I want to do is, Naman sir, how to solve 3-phase unbalanced load, as they can't be solved in per phase basis. No, they can be solved in per phase basis. What's the problem? If the load is unbalanced, let's say the resistances are unequal, so it doesn't matter. You have selected the base value like this. This is the base value. If you know the base value, then from this base value you can calculate the Z base. So let's say this is 90, this is 80, this is 70. So you divide it with 50, so the per unit value will be different. Okay, in each phase per unit value will be different. Okay, we are taking load unbalanced, not the source. Source unbalancing is not taken care. Okay, I am taking load as unbalanced load, so it doesn't matter. If load is taken as unbalanced load, it doesn't matter. Okay, as soon as this source is balanced, the Z base will remain same. If the load is unbalanced, on every phase what you can do is you can divide it with Z base, because Z base came out to be same because the source is balanced. Okay, I hope you understood it. Now let's come to the next thing. Now let's come to this source point. Let's say we have sources, and these sources, the value of these sources is given in per unit case. Now tell me the line voltage. This is VAN. This is VAN in per unit. This is VBN, and this is VCN. So these values are given in per unit. Now can you tell me what is the line voltage? What is VAB here? It will be VAN minus VBN. Tell me, guys. VN minus VBN. So it will be 1 angle 0 minus 1 angle minus 120. Fine. Now it should be root 3 angle 30 degree. Is it correct or not? Tell me, guys. Is it correct or not? So the per unit value has to be root 3 times. No. In star connected system, if you are looking, if the per unit values of the phase voltages are given to you, and you want to calculate the per unit value of the line voltage, then it should be like this: VN minus VBN. You have subtracted the per unit value, and then you can calculate the per unit line voltage. Is it correct or not? Tell me, everyone. Is it clear or not? Is it correct or not? Tell me. No, sir, it is not correct. This is wrong. Why it is wrong? Why it is wrong? Tell me, guys. This is wrong. Because the problem is, whenever you take the differences of any two quantities, let's say you are taking difference of VN minus VBN, then don't take the difference of per unit values. It will give you a wrong answer. Okay? Whenever you are taking difference, especially in 3-phase system, Let's say you are taking the voltage difference in three-phase system or maybe current difference in three-phase system. Don't use the per unit value to take this difference. It will give you a wrong answer. Why it is wrong? Why it is wrong? Let me tell you why. Let's say I have a circuit like this. Let's take a star connected source. Let's take a star connected source. Okay. Let's take a star connected source. And let's put the actual value. Let's take the actual value of these sources. Let's say this is 100 angle 0. This will be 100 angle minus 120. This is 100 angle plus 120. These are the actual values. Okay. And this is the neutral point. This point is A, this point is B, and this point is C. Okay. A, B, C. Now, can you calculate VAB? So VAB came out to be root 3 into 100 angle 30 degree. Okay, this will be my VAB. Line voltage is root 3 times of the phase voltage. We know that. Now, what I want to do is I want to convert these phase voltages and line voltages in per unit. I want to convert them in per unit. Now, how I am going to do that? You have to take the base. You have to select the base value. Let's say the base value of the phase I am selecting as 100 volt. If the base value of the phase is 100 volt, then what is the base value of the line voltage? The base value of the line voltage, I am saying the base voltage per phase as single phase voltage. Okay, let's not write it single phase, or maybe you can write it like this. Base voltage of phase I have selected 100 volt, then the base value of the line voltage will be 100 root 3. Is it fine, guys? Tell me, is it clear? If you are selecting base voltage of the phase, then let's say it is 100 volt, then obviously the line voltage base will change to 100 root 3. Okay. Now, please convert this in per unit. So if you are converting this in per unit, divide it with base value, it will become 1 angle 0. It will become 1 angle minus 120. And it will become 1 angle plus 120. Clear? These are the phase voltages in per unit. Now in line voltage, look at the line voltage. Actual line voltage is this. Now you have to convert this in phase. Convert this in per unit. How to convert this in per unit? You have to divide it with the base value. And the base value in the line is 100 root 3. So you have to divide with 100 root 3. So it will become 1 angle 30. Okay, it means the line base value, line per unit value will also remain 1. If the phase per unit value is 1, 1, 1, you can see, then the line per unit value will also remain 1. That's why I am telling you that this is wrong. This is wrong. You can't take difference like this. Okay. So you have to be careful. If the phase voltage per unit values are provided to you in star system, then the line voltage per unit value will also remain 1. So this is 1, this is 1, this is 1. Line voltage will also remain 1. Is it fine, guys? Have you understood it? Only the angle will change. Only the angle. Angle can be taken from this. Angle will be 30. Okay. But the per unit value will remain as 1. Is it clear, everyone? Tell me. Have you understood it? Say yes or no. Tell me, guys. Is it clear or not? Tell me, everyone. Is it clear or not? Say yes or no. Is it clear or not? Tell me, everyone. Now let's take one question. I want to take one question. And the question is, let me give you one question. Let's see how many of you can solve it. Question is, I have a star connected system like this. These sources are connected in star. These sources are connected in star, and let's say this voltage is 1 angle 0 per unit. This voltage, and let's say this is grounded. This voltage is 0.5 at an angle of minus 60 per unit. And this voltage is 1.2 at an angle 120 per unit. Okay, per unit. And the voltage base value, V base, for three-phase circuit is given as 100 root 3 volt. 100 root 3 volt. Okay, 100 root 3 volt is the base value of three-phase system. Now I want to calculate, find line voltage per unit line voltage. Find per unit line voltage. Tell me, guys, how to calculate. Find per unit line voltage. Line voltage VAB. Let's call it A point, let's call it B point, and let's call it C point. I need to calculate per unit line voltage VAB. What is the value of this line voltage VAB per unit? How to calculate this? Tell me guys, how to calculate the per unit line voltage for the phase A and B? How to calculate it? Obviously, what you need to do is, you need to take VAN minus VBN, fine? VAN minus VBN. Now, if you take the difference, VAN minus VBN, if you do like this, you can't take per unit values. You can't subtract per unit values. Remember this point. Otherwise, you are doing the mistake. Okay? Is it fine, guys? Have you understood this point? Say yes or no. You can't take that VAB will be equal to 1 angle 0 minus 0.5 angle minus 60. This is wrong actually. If you are calculating the per unit value of VAB like this is wrong. Now how to solve it? How to solve this question? What you can do is, if you know the base value of the three-phase circuit, in case of three-phase circuit, the base value is this. It means this is the base value of the line voltage. Now what is the base value of the phase voltage? The base value of the phase voltage is 100 volt. Okay. The base value of the phase voltage is 100 volt. So what you can do is, since the base value of the phase voltage is 100 volt, you can multiply them with 100 so that you can get the actual value. Okay. So that you can get the actual value. So if you get the actual value, if you can get the actual value, then what is the actual value, guys? The actual value for this source will be 100 angle 0, and the actual value for this source is 50 angle minus 60. Is it fine? This is A, this is B, and this is grounded. Now you can calculate VAB. Now you can calculate VAB. What is VAB now? How to calculate VAB? Okay. Tell me guys, only for voltages. No, Arun, what do you want to say? Okay, so now what we have done is, we have calculated the phase voltage. So phase voltage base is 100 and multiply the per unit value with the base value so that we can get the actual value. So you have got the you got the actual value. Now you can calculate VAB. VAB is VN minus VBN. 100 angle 0 minus 50 angle minus 60. Is it fine? So it came out to be, let me calculate this value, 100 angle 0 minus 50 angle minus 60. Okay, this came out to be 86.60 at an angle of 30. Okay, this is the actual value of the line voltage. Now what you can do is, now you can convert it in per unit. How to convert this in per unit? You can divide this voltage with this line voltage, okay, with this base of the line voltage. So the per unit value, VAB per unit, will be equal to, tell me, what is VAB per unit? It came out to be 86.60 divided by 100 root 3, okay. This much of per unit is the answer. VAB per unit is this answer. So please calculate this value. You can divide it with 100 root 3, okay. You can divide it with 100 root 3. So the answer came out to be half, 0.5, okay. This came out to be half, okay, 0.5 per unit. Now let's say you take the difference here directly. If you take the difference, if you take the direct difference, then it will be 1 minus 0.5 at an angle of minus 60. If you are taking the direct difference, the answer will be different. Answer will be root 3 by 2. Root 3 by 2 per unit. Okay, this is wrong answer. This is wrong. Okay, why it is wrong? I have told you. Whenever you need to take the difference of the per unit values, you don't take the difference. Remember, you don't take the difference like this. Okay, don't take the what you need to do is, you convert them in the actual value. Once you get the actual value, take the difference now, and then you convert it in per unit. Okay, is it clear, guys? Tell me, have you understood this? Say yes or no. Tell me everyone, is it clear? Is it clear? So I told you about how to tackle this this per unit case, okay, in case of star connected system. Now let's come to the delta connected system. Now what about the current? What about the current in star? Current, it doesn't matter, because the line current and the phase current remain the same. So there is no need to take the difference, okay. Because in current we don't take the difference. No, we don't need the difference actually, because in star connected system, whatever current, whatever the line current is, the same the phase current will be there. Okay, so that's why in delta you don't care about the current, only thing is voltage. So you have to be more careful about the voltage in star connected system. Now in delta, let's say you know the current value. Let's say you know the current value. Let's say this current is 1 angle 0 per unit, and this current is 1 angle minus 120 per unit, and let's say this current is 1 angle plus 120 per unit. Now what is this current, guys? And what about this current? And what about this current? What about this current? Now you can calculate it easily. Don't take the difference in per unit. If you are looking, if you are saying looking that we can apply the KCL at this point, so you have to take the difference of the current. Now this current minus this current will be this current. So you don't take the difference in per unit. Remember this point. Let me tell you, the current which will come out from this has the per unit value as 1. Angle will change only. Okay, but if you take the direct difference, this will not be 1. It will be root 3. Okay, it will be root 3 if you take the direct difference. This current minus this current, if you are doing, you will get root 3 here. So this is wrong actually. So remember, in case of delta, the phase current and the line current will have the same per unit value if the system is balanced. If the system is balanced, then you can say the line current and the phase current has the same per unit value. Okay, it's similar to the voltage case. Similar to the voltage case. In star, the voltage per unit values are given to you. If you want to convert them in delta, if you want to calculate the line voltage, while calculating the line voltage, don't do this. Okay, the line voltage per unit value will also remain 1 per unit. I have proved that. Okay, the line voltage per unit value will also remain as 1 per unit. Only the angle will change. Similarly, in delta, the current, because in delta we take the difference of the current. If the phase current are 1 per unit, then the line current will also be at 1 per unit. Remember this point, otherwise you will make mistake. Is it fine, guys? So in star and delta, you have to be careful about this. Now let's try to solve one question. Okay, the question is like this. You have is 100 ohm, 100 ohm and 100 ohm, and let's say the rating is 100 kV is to, let's call it 50 kV. 100 kV is to 50 kV, okay, and the rating is 500 kVA. What I need to do is, I need to find the per unit value of this current IA. I need to calculate the per unit value of this current IA. How to calculate the per unit value of this current? There are two ways. What are those two ways? First way is, better you calculate the actual current, actual line current. Once you get the actual line current, on this base, you calculate the base line current on this side, on the high voltage side, you calculate the base line current and then divide it. I mean, the actual divided by the base, you will get the per unit value. Or you can also solve the same question in per unit system. You can also solve the same question in per unit case. In per unit case, you can directly tell the answer. Okay, you can directly tell the answer. Let me tell you how. First of all, please tell me what is the Z base here. What is the power base on this? What is the base value on base voltage and base power on this side? Let's select transformer rating as the base. So on this side, 50 kV is the base voltage and 500 kVA is the power base value. And remember, this is 3-phase voltage and this is 3-phase power. Okay, now I need to calculate Z base. Now tell me how to calculate Z base. To calculate the Z base, I have to look at the single phase situation. What is the base voltage across it? This is the line voltage base value. If this is the line voltage base value, what is the phase voltage base value? Phase voltage base value will be 50 by root 3 into 10 is to power 3. Okay, you have to take the square of this, divide by single phase base power. The single phase base power is 500 into 10 is to power 3 divided by 3. This is my single phase base power. Is it clear, guys? So we have calculated single phase base voltage and single phase base power. You take the ratio, you will get the Z base. This is cancelled and you will get 50 into 50 into 1000 divided by 500. Okay, if you can simplify this, you'll get this. So this 2 will be this, okay, this is cancelled. So Z base is 5000 ohm. Z base came out to be 5000 ohm. If Z base is 5000 ohm, you can convert this in per unit. So the per unit value came out to be 100 upon 5000, that is 1 upon 50. 1 upon 50 per unit. This is the resistance value. Okay, this is the resistance value. Now I need to calculate the per unit current. What is this per unit current? Tell me, guys. What is this per unit current? How to calculate? If somehow we can calculate per unit voltage, if somehow we can calculate the per unit voltage here, divide by the per unit resistance, you will get the per unit current. What is the per unit voltage? The actual voltage across this is 50 by root 3 kV. Actual voltage is this, and the base value is also same. The base value across this phase, base value of the phase voltage is 50 by root 3 again. So you can say that the per unit voltage across this phase is 1 angle 0. Okay, so the current value will be 1 angle 0 divided by 1 by 50. So this current has to be 50 angle 0. Is it fine, guys? Is it fine, guys? I think I have done the mistake with the angle, or it's correct. If you are okay with the magnitude, I'm fine, but actually the angle is not correct, but angle is not required. Okay, so you don't worry about it, because what I have done is I have taken the angle of this phase voltage equal to 0. So the line voltage angle has to be at 30 degree. This voltage angle has to be at 30 degree, but anyway, it's not wrong. You can take this angle as reference angle. Okay, so no problem. So we have calculated this current as 50 per unit. This current is 50 per unit. Is it fine? This is 50 per unit. So this is also 50 per unit, and this current is also 50 per unit. Fine. Now tell me, if you know this coil current, this is 50 per unit, what will be this coil current? Tell me, guys. It will also be 50 per unit. It will also be 50 per unit, because while referring the per unit value, current will remain same. The per unit value will remain same. Okay, if you want to refer the current value, the per unit value will remain same. It will not change. So this is 50 per unit. This is also 50 per unit, and this will also be 50 per unit. Now tell me what do you want to do? You want to calculate this current. This is delta connected system. I told you in delta connected system, if the current is balanced, whatever the phase current per unit value, the same will be the line current per unit value. So it has to be 50 per unit. Is it fine? So answer is 50 per unit. Answer came out to be 50 per unit. Okay, this IA has to be 50 per unit. Now you can also calculate the actual value of this current. How to calculate the actual value of this current? How to calculate the actual value? You can multiply this per unit value with the base current of this side. You can calculate the actual value. Okay, so it's very easy. It's very easy. We have calculated this current as 50 per unit. This is also 50. This is also 50. I'm not interested in angle. Okay, since you know this current, this coil current, from this coil current you will get this current. In this dot it is entering, from this dot it will leave. If it is 50, it will also be 50, because in per unit you don't refer with respect to turns. In per unit case, the current per unit value will remain same on both sides, and voltage per unit value will also remain on both sides. Impedance per unit value will also remain same on both sides. So what you can do is, this current is per unit, this current is also per unit, this current is also 50 per unit. Whatever the phase current per unit is in delta, same will be the line per unit value in balanced delta. Okay, I have told you here, na, if the phase per unit value is same, okay, then the line per unit value will also remain same. I hope it is clear to everyone. Is it fine, guys? So this way you can solve this question. Now let's come to the next question. This is the next question, guys. This is the next question. What is this question, guys? In this question, for a circuit shown below, the circuit is given like this. This phase voltage is 38.1 kV. Wait a minute, I think there is a correction in this question. This voltage has to be 3.81 kV. This is not 38. Let me remove it. 3.8 kV. This voltage is given as 3.8 kV. 3.81 kV. Okay, so the question is, the circuit shown below, for the circuit shown below, the circuit is given like this. This is 3.8 kV. This is also 3.8 kV. This will also be 3.8 kV. This is 0.6, 0.6, 0.6. Now find the resistance of each phase of load seen from the Y side of the transformer. Okay, if you are looking on this side of the transformer, what should be the resistance value which is seen by the Y side of the transformer? And there are 4 options. We need to calculate the resistance value in per unit. You can see that the resistance value is in per unit. Now how to calculate the resistance value in per unit? It's very simple. Let me tell you. Let's say that this voltage is 1 per unit. If in delta, if this voltage is 1 per unit, I call it 1 per unit, 1 angle 0, let's say. Okay. So this voltage will also be 1 per unit because this coil is coupled with this coil. So I told you, if this is 1 per unit, this will also be 1 per unit, because in per unit case we don't refer. Okay. In per unit values, the values will remain same. The voltage value will remain same. If in per unit, this voltage is 1 per unit, this coil is coupled with this coil. So this phase voltage, if you can take this phase voltage as the base voltage, then this can be converted to this base voltage. Okay, the base voltage will transfer, the base voltage will change, but the per unit value will remain same. Okay, if this is 1 per unit, this voltage will also be 1 per unit. Okay, because this coil is coupled with this coil. Now, what is the per unit current? What is the per unit current? If somehow we can calculate the per unit current, what is that? What is the per unit voltage here? Can you calculate the per unit voltage across them? What is the per unit value voltage across them? In delta, this is my line voltage. This is my line voltage, and I have taken this voltage as the base voltage. But remember, this is the line voltage as well as the phase voltage across this coil. Okay. So the base voltage is 3.81 kV on delta side. Here the base voltage is 3.8 kV. But this phase voltage will become the line voltage across the load. Okay. Because across the load, if you look at this point is connected here, this point is connected here. So what you can say is, this phase voltage will become line voltage here. Is it fine, guys? It is a line voltage here. Okay. Now, if it is a line voltage, then what I need to do is, I need to calculate the phase voltage. Across them. So the voltage across this resistance will be 3.81 by root 3. Okay, 3.81 by root 3 kV. This will be the voltage across this resistance. If this is the base voltage across here, then this will be the base voltage across here. Across this resistance, this will be the base voltage. Okay. If this is the base voltage here across this phase, then the base voltage between these 2 points will again be 3.81, but the base voltage across this phase will be this voltage. Okay. It means, let's say this is 1 per unit. So this voltage will also be 1 per unit. I don't know whether you have studied, whether you have understood it or not. Or there is one more way. To understand it. What is that way? Better you convert this star into delta. Okay. Better you convert this star in delta. Let's convert the star in delta. Okay. If I convert this star in delta, then the secondary side will look like this. The secondary side will look like this. The secondary side will look like this. Here you have the dot and the dot. Okay. Now the secondary side, now the resistance value, let's call it A point, B and C. Okay. Now tell me the delta resistance is, what is the delta resistance value? This plus this, so it will be 1.8 ohm. Okay. So the delta resistance came out to be 1.8 ohm. You can connect it like this. Okay. Every resistance is 1.8 ohm. Fine. Now, what you can do is, now tell me, if this is 1 per unit value, 1 angle 0, let's say, if this is 1 per unit value, this voltage will also be 1 per unit. This voltage will also be 1 per unit because this is in parallel. So, if somehow we can calculate its per unit value, then current voltage per unit value divided by the impedance current value, you will get the, the voltage per unit value divided by the resistance per unit value, you will get the current per unit value. What I have done is, first I have changed this star in delta. Now I want to convert these resistances in per unit. How to convert these resistances in per unit? That's very simple. What is the Z base? So Z base came out to be, what is the base voltage across it? Base voltage across it is 3.8 kV. So 3.8 into 10 is to power 3, take the square of this, divide by the power base, per phase power base. What is the per phase power? Per phase power is the rating of the transformer. Is it given? No, it's not given. It should be given, na? The rating. Let me check the MVA rating or the KVA rating. Wait a minute, guys. It's 75 MVA. Okay, it's 75 MVA. 75 MVA. So now the per phase power is, on this side the per phase power is 25 MVA. So what you can do is, the voltage, the base voltage across this resistance is 3.81 kV. I have taken the square of this, divided by the 25 into 10 is to power 6. Is it fine? Per phase power. That's how I calculate the Z base. Okay, so it will be equal to 3.81 into 3.81 into 10 is to power 6 divided by 25 into 10 is to power 6. Okay, this is cancelled here, so it will be 3.81 square upon 25. Okay, this will be my Z base. This will be my Z base. I have calculated the Z base. Now, if you simplify it, it will become 3.81 square divided by 25. It will become 0.58. 0.58. Is it fine? 0.58. Yes. This is the Z base. Now, what I need to do is, I need to convert this in per unit. So 1.8 divided by the Z base, 0.58. What is the Z base value, guys? 1.8 divided by 0.58. It will be 3.10. So the resistance value is 3.10 per unit. This is the resistance value. Fine. Now can you calculate the current, the per unit current in this resistance? Yes. The per unit voltage across it is 1 per unit. Now the per unit current will be 1 divided by 3.10 per unit. This is the current we have. Okay, this is the current we have. So we have calculated the per unit current here. If you know the per unit current in the delta, in this wire, if you know the per unit current, this wire, this current will also be 1 upon 3.10 per unit. Because I told you in delta, whatever the per unit value in the phase, the same will be in the line. Okay, you can't multiply it with √3. Remember this point. So this per unit current has to be 1 by 3.10 and this per unit current has to be 1.310. Okay, because in delta, the per unit current in the line, if the system is balanced, the per unit current in the line and the per unit current in the phase will remain same. Okay, it will remain same. Simple. So you can see that this per unit current has to be 1 over 3.10. So now this current, we have calculated this current has to be 1 over 3.10 per unit. Whatever the line current is, that per unit value will remain same in the phase. So this is 1 over 3.10 per unit, and if this is the per unit value of the current in this coil, now you can say that the current in this coil will also be 1 over 3.10 per unit. Is it fine? So we have calculated the current in this coil in per unit value. Okay, this is the per unit current in this coil. What is the per unit voltage across this coil? Per unit voltage across this coil is this. Now how much resistance this coil will see? The resistance seen by this coil is the voltage across the coil divided by the current. Is it fine? So it will be 3.10 ohm, 3.10 per unit. Okay, so the resistance seen will be 3.10 per unit. I hope it is clear. Okay, so every coil will see the resistance of 3.10 per unit. So the answer is Agra. Answer is Agra. Okay, 3.10 per unit. Please try to understand this question, because this is again very interesting case. This is again very interesting case, because many students will do the mistake here. Let me repeat again. What I have done is, first I have converted this star in delta. Okay, I have converted this star in delta. Then I have calculated this Z base. How to calculate the Z base across this? Tell me guys, how to calculate the Z base? To calculate the Z base, look at this phase voltage. What is this phase voltage? Voltage across this phase. Voltage across this phase is 3.81 kV. Okay, because whatever voltage, actual voltage you looking here, the same voltage will appear here. It is 3.81 voltage, 3.81 kV. So 3.81 kV, take the square of this, divide by the per phase power. Now the actual 3-phase power is 75 MVA. So I have divided with 3, so it will become 25 MVA. Is it fine? So I have divided like this. So I have calculated ZB like this. This is my ZB. ZB came out to be 0.58. Z base came out to be 0.58. Now what I have done is I have converted this in per unit value. So this resistance came out to be 3.10 per unit. In per unit case, this resistance is 3.10. Now what I need to do is I need to calculate this per unit current. We know that the voltage across this is 1 per unit. Here the voltage is 1 per unit. Here also the voltage is 1 per unit. Divide by the per unit resistance, you will get this per unit current. If in delta, you know the per unit current, and since the delta is balanced, you can say this line current will also be the same. Okay, I told you that. I told you before that in delta, the current per unit value will remain same. So if this is 1 over 3.10 per unit, this current will also be 1 over 3.10 per unit. If you know this current will also be known to now. I mean, the per unit value will again remain same. We can calculate the coil current. If this is the line current, you can also calculate the phase current. So in case of per unit, in delta, per unit value will remain same. So this current will also be 1 over 3.10. It means we know this coil current. If you want to refer this current in this coil, because this coil is coupled with this coil, so if you want to refer this per unit value on this side, the per unit value will remain same. It is 1 over 3.10. This will also be 1 over 3.10, and the voltage across this coil is 1 per unit. So this voltage will also be 1 per unit. Okay, because in per unit value, the values will remain same. Whenever you try to refer them, values will remain same. Now you can see that since the voltage across this coil is 1 per unit and the current is this, so you take the ratio to calculate the resistance seen by the coil. So the resistance seen by the coil is 3.10 per unit. Okay. Sir, unbalanced voltage can also be subtracted in per unit. No, let me tell you, whenever you need to subtract the voltages or current, don't subtract them in per unit. Don't subtract in per unit. Wherever you need to subtract the voltages, or you need to take the difference of the current, or wherever you need to add the voltages or add the current, then what you need to do is first you need to calculate the actual value. Okay, subtraction and addition should not be in per unit. Remember, especially in three-phase system. Especially in three-phase system, in single phase no problem. In single phase there is no problem. We have already done that. If you remember, let's come back to the single phase case. In single phase, if you remember, I have added these voltages in per unit case. I have added these voltages in per unit case, and I have calculated this Vs. So in single phase system, there is no problem if you are adding the per unit voltages or per unit current, no problem at all. But in case of three phase, don't try to add the per unit value directly. Okay. Whenever the per unit value of different phases are added or subtracted, don't do it in terms of per unit. Better you take the actual value, calculate the actual value, and then convert the actual value back to the per unit value in case of unbalanced system. Because in balanced system, it's directly, I mean, you can say directly. In balanced system, whatever the phase voltage is, whatever the phase current, whatever the phase voltage is, the same voltage will be the line voltage in per unit. Okay, you don't need to do any calculation. You just remember this point. Okay, I hope it is clear to everyone. Okay, and I hope this topic you have understood well. Now let's come to the single line diagram. In power system, we require single line diagram. Okay, and for the single line diagram, we need to plot the reactance diagram. So I think it's easy part. You can do it yourself. You can plot the single line diagram and the reactance diagram then. So I'm not covering this topic. This is not that much important, but you should know how to draw the reactance diagram when a single line diagram is provided to you. What is the meaning of single line diagram? Basically, what happens is, let's say this is generator. So you can wait a minute. Okay, let me tell you what is single line diagram. In single line diagram, what we have is, let's say this is motor, this is motor, okay, and here you have a transmission line, okay. Let's make them, oh wait, okay. So now what we have is, we have one generator, two motors. Let's say this generator is star connected with the neutral grounded via reactance. This transformer is Y delta transformer, okay, and the Y is grounded to neutral, okay. Y delta transformer is this, and then you have delta Y transformer, okay. Here you have the motor, okay, this is Y connected, this is also Y connected with neutral grounded, okay. Now this is my single line diagram. It means the entire power system is shown like this: one generator, two motor, and there is a transmission line. So I'm not going to show the every phase. I'm showing everything in single line. We call it single line diagram, okay. This is called single line diagram. Now we need to draw the reactance diagram of this situation. We need to draw the reactance diagram. How to draw the reactance diagram? How to draw the reactance diagram? We have to write the per unit value of this synchronous reactance of this, and then leakage reactance of this transformer, and then line reactance of this this transmission line, and then leakage reactance of this transformer in per unit. So first of all, you have to define the base in the entire system. How you are going to define the base? Let's say you define the base on the generator side. On generator side, let's say 13.8 kV is the base voltage, and 200 MVA is the base power. So the power in every region will remain same. The base power will be fixed. In every situation, in every region, the base power is fixed. On this side also, the base power is 200 MVA. Now, we need to check the voltage. On this side, the voltage is 13.8 kV. Okay. Now, what is the base voltage on this side? You have to look at the transformer. The transformer will change the base voltage. Okay. Let's say this side is star connected and this side is delta connected. And this transformer is, let's say, 13.8 kV to 138 kV. It means this transformer is changing 13.8 kV to 138 kV. It means the base voltage on this side has to be 138 kV. These are the line voltages. Remember, in transformer, this is not turn ratio. This will not give you the turn ratio. These are the line voltages. And in star delta transformer or delta star transformer, the ratio of the line voltage will not be the turn ratio. Remember this point. Okay. So now what you can do is you can refer this 13.8 to this side, so it will be 138. So the base voltage will be 138 kV on this side. Now you have a delta star transformer. Let's say this delta star is 138 kV to 13.8 kV. So it means this voltage will change the base 138 to 13. So on this side, base voltage is 13.8 kV. Is it fine, guys? So we have to write the base first. We have to define the base first. On one side, let's say the base is given, then using this base, you can write the entire base of the system. I mean, in this region, you can calculate the base, and in this region, you can calculate the base. Once you get the base value, then whatever the reactance values of leakage reactance of this transformer and the internal reactance of this generator, you have to convert them in per unit. Okay. You have to write them in per unit. And then you have to draw the reactance diagram. Let's say this is my generator. So for the generator, you have to write this reactance in per unit. It might be possible that this generator reactance is provided to you at the same base. So you don't need to convert this impedance value, this reactance value. But let's say for the transformer, the power is, let's say, the power rating of the transformer is 500 kVA, 500 MVA, let's say, and the leakage reactance is J 0.5 per unit. Let's say this is given like this on its own base. Now, if I want to show the reactance of the transformer here, because after generator you have to show the reactance of the transformer. So if you want to show the reactance of the transformer, then what you need to do is you need to change this per unit value, because this per unit value is on this base, on the transformer base, and the base already has changed. On the high voltage side, if you look at the base is 200 MVA and 138 kV. On the transformer, this per unit value is given at 138 kV, 500 MVA. So this value is at different base. We need to convert this on this base. How to convert this? It's very simple. X per unit old, X per unit new is equal to X per unit old into V base old divided by V base new, take the square of this into S base new divided by S base old. Okay, use this formula and you can convert this per unit value on new base, or this per unit value on the new base, you can convert it and you can use that value here. Similarly, you have to show the reactance of the transmission line. You have to show again, you have to show the reactance of the transmission line, and then you have to show the transformer again. Okay, and then there are two motors. So there are two motors, you have to show the reactance of these two motors. Is it fine, guys? This way you can plot the reactance diagram. This way you can plot the reactance diagram. I hope it is clear. The only thing is you have to convert the reactances of these motors and transmission line and transformer on the common base, on this base, on the base provided to you, on this base, because it might be possible that the reactance of the transformer given is at different base. The given reactance is at different base. You have to convert this on this base. So you can convert it and you can show it like this. This is transformer, this is transmission line, this is again transformer, and these are two motors, and this is generator. Okay, so this way you can draw the reactance diagram. I hope it is clear to everyone. This is not that much important, but still you should know how to write, how to make the reactance diagram. Now this chapter is completed. I am going to the next chapter. So I have completed the per unit system. Okay, now I want to go to the next chapter, that is calculation of Y bus and load flow studies. Okay, so the chapter name is load flow studies, and in the first topic in the load flow studies, we have to calculate the Y bus. We have to find the Y bus. Let's say this system is provided to you. What is the Y bus of this system? How to calculate the Y bus and Z bus? To calculate the Y bus or the Z bus, it's simple. What you can do is you can apply the nodal analysis. You can apply the nodal analysis. Let's call it V1. The voltage at this bus 1 is V1, and this is V2, and let's call it V3. So there are three bus system. One is reference bus, you can say. This is ground. Okay, so this is V1, this is V2, this is V3. Now what you can do is you can make the Y bus like this. First of all, Y11. How to write Y11? Y11 means, look at the bus number 1. At bus number 1, how many branches are connected? 1 and 2. Only 2 branches are connected. So what you can do is you can take their reactances in opposite way, like this. J 0.5 plus 1 upon J 0.4. Is it fine? This is my Y11. Now, what is Y12? Oh, I need to write Y12. How to write Y12, guys? If you want to write Y12, look at the mutual branch. This is bus number 1, this is bus number 2, and this is the mutual branch. While writing Y12, we'll use J 0.5. Since it is a mutual, so write with negative sign. Okay, and this reactance has to be written in opposite way. Now what is Y13? If you look at Y13, there is no mutual connection between 1 and 3. There is no direct connection. There is no direct connection. So it has to be 0. Okay, it has to be 0. So I have written Y11, Y12 and Y13. Now let's come to Y21. How to write Y21? How to write Y21? Y21 means, since 2 and 1, you have to use the mutual branch. 2 and 1, follow the subscript, 2 and 1. So Y21, how to write Y21? Look at the mutual branch. So the mutual branch has this reactance. So since the mutual is there, so I have to take negative sign and J divided by 0.5. This is Y21. Now what is Y22? Look at the junction number 2. How many branches are connected? 1, 2 and 3. So you reciprocate them and then add them. So it will be 1 over J 0.5 plus 1 over J.5, 1 over J.1 plus 1 over J.5, because there were 3 branches, no? These 3 branches were connected at this junction. So what you can do is 1 over this value plus 1 over this value plus 1 over this value. This way you can write like this. This is Y22. Now Y23. What is Y23? Again the mutual branch is used. And since you are using the mutual branch, that's why you have to take negative sign, divide by the opposite of this, J 0.5. Is it fine, guys? So this way you can write Y23. Now let's come to Y31. What is Y31, guys? What is Y31? 31. There is no mutual branch between 3 and 1. So it's 0. Y32. 32. I have to write minus 1 divided by J 0.5. This is Y32. Now Y33. look at this junction, look at this bus, and there are two branches connected here. So just take the opposite of that, 1 over j 0.5 plus 1 over j 0.4. I hope it is clear. Okay, so this is my y bus. I have calculated y bus. Okay, so this way you can calculate the y bus of the system. It's easy peasy. Now the problem is we have to eliminate some node. How to eliminate the node? How to eliminate the node? Tell me guys. How to eliminate the node, and which nodes we have to eliminate? Which node you can eliminate? Now you can see that. First of all, let's simplify it. Let's simplify it. So if you simplify it, you will get, tell me, what is y11? Y11 came out to be minus j2 minus j2.5. So it will become minus j4.5. This is minus j4.5. What is this? It will be plus j2. It is 0. This will be j2. This will be 0. Now this is minus j2, and it will also be minus j2. It will be minus j10. So it will become minus j14. Is it fine, guys? And this will be minus j2. Okay, plus j2. This will become plus j2. It will be plus j2. Now this is 0. This is j2. What about this element? This element is minus j2 and minus j2.5. So it will be minus j4.5. This is my y bus. Okay. We know that y bus into the bus voltages V1, V2, V3. V1, V2, V3 must be equal to entering current. Must be equal to entering current. If you know the nodal equation, you should know how to calculate the entering current. Look, if you want to convert this in current source, then this source will provide a current in upward direction. If you can convert this in current source, then the current source value will be EF1 upon this value. EF1 upon this value. This will be the entering current in node 1. So the entering current in node 1 is, let's call it I1. What is the entering current in node 2? There is no source connected at bus number 2. There is no source connected in bus number 2. So you can say that the entering current is 0. And the entering current in bus number 3 is due to this source. You can convert this source in current source, that is EF2 divided by this value. It will be the current source which will be entering current in this junction. I call it I3. Is it fine? Now, since there is no entering current in bus number 2, you can eliminate bus number 2. How to eliminate bus number 2? How to eliminate this bus number 2? What is the elimination method? If you want to eliminate any row, let's say you want to eliminate some, let's say some bus. Let's say there is a y bus system. Let me tell you. Y11, Y12, Y13, Y31, Y21, Y22, Y23, Y31, Y32 and Y33. Okay, let's say you want to eliminate the last row. Okay, let's say you want to eliminate the third bus. Then how to eliminate the third bus? How to eliminate the third bus? Now the resultant will be 2 by 2 matrix. Only 2 buses will be there. In the y bus matrix, only 2 buses will be there because you want to eliminate the third bus in this system. Let's say you want to eliminate third bus. Don't take this into your mind. I'll come back to this, because in this case I want to eliminate the bus number 2. Why? Because the entering current at bus number 2 is 0. So you can eliminate that bus. Whenever in any bus, let's say the entering current is 0, you can eliminate that bus. But how to eliminate that? I'm telling you the process. So let's take a separate case. Let's take a different case. I'll come back to the original situation. Let's take a different case. Here in this case, the y bus is 3 by 3 matrix. We know that. And we want to eliminate, let's say, bus number 3. Now, how to eliminate bus number 3? How to eliminate this bus number 3? Obviously, if you eliminate bus number 3, only 2 buses will be there. And the matrix will be of 2 by 2. What should be the element value? Y11 new. Okay, Y11 new. Y12 new. How to calculate these value? Y21 new and Y22 new. What will be the new value of these? Okay, now how to calculate these values? There is one expression. What you can do is, let's say you want to calculate Yjk new. Let's say the matrix is n by n matrix. Okay, let's say we have n by n matrix. N by n matrix. And the last element this element is YNN. Okay, and there is some element YJK. You want to calculate the new value of this YJK. So YJK new will be equal to YJK old minus YJN into YNK divided by YNN. This way you can calculate the new YJK. Okay, I have already written like this. Okay, so this way you can eliminate the row. You can eliminate the row. Now in this question, let's say you want to calculate this Y11 new. So Y11 new will be equal to Y11 old, whatever the old value is, Y11 old minus Y1N, N is 3 here. So Y13 into Y31 divided by Y33. Okay. This way you can calculate Y11 old is this value. This is Y11 old. Y13 is this value, and Y31 is this value divided by Y33. This way you can eliminate, this last row. So you can calculate Y11 new, Y12 new, Y21 new, and Y22 new. Let's say you want to calculate Y22 new. So what will be the Y22 new? Y22 new will be equal to, Y22 old minus Y23 into Y32 divided by Y33. This way you can calculate Y22 new. I think it's easy peasy. Okay, this way you can calculate Y22 new and Y11 new. It's easy peasy. Now the thing is, now let me tell you one more point. So I told you how to eliminate, but there is one more interesting point. The node which you want to eliminate, you have to take that node at the last. Let's say in this case you want to eliminate node number 3. That's why the node number 3, the Y31, Y32 or Y33, I have written at the last. Okay, because you want to eliminate node number 3. So node number 3 has to be at the lower point. Okay, if you want to eliminate node number 3. And remember, the node in which the entering current is 0, you can eliminate that node. Now in this question, if you look at this carefully, in this question, the entering current in the bus number 2 is 0. The entering current in the bus number 2 is 0. So we want to eliminate bus number 2. So first what I need to do is, I need to write this bus number 2 at the last. Okay, I have to switch this bus. I have to shift this. Okay, so that it can be written at the lower point. Now tell me how to write it. How to write this? If you want to switch this bus at this position, okay, so first switch it. If you want to switch it, then it will be like this: minus J 4.5. This is J2. This will be 0. This will be 0. This is J2. This is minus J 4.5. This is J2. This will be minus J14, and this will be J2. So what I have done is, I have switched this row number 2, and I have changed these two rows so that this row came at the last. But the problem is, this is not correct. Why? Whenever you are switching this now, whenever you are replacing row number 3 with row number 2, you are replacing row number 3 with row number 2. Okay, now you have to replace the column number 3 with column number 2 also. You have to replace the column number 3 with column 2 also. It means not only you have to replace the row with the row, but you have to replace the column with the column. Okay, so it means you have switched this now. The row is replaced, the second row is replaced with the row number 3. So 3 will come upward and 2 will go downward, since it has 0 entering current. So you can take it down. If you take it down, it will be like this. Now you want to switch, you need to switch the column also, the second column with the third column. Okay, not only the row, the column will also be changed. Okay, so you have to remember like this. Now if you switch the column also, then it will be like this. It will become minus J 4.5. This is 0, obviously. Okay, this will be 0, and this is J2. Now it is 0, and it will be minus J 4.5. It will be minus J 4.5, and this J2 will come here. This will be J2. Now this is J2, and here this J2 will come here, come at this position, and this will be minus J14. Is it fine, guys? So what I have done is I have changed row 3 with row 2 and then column 3 with column 2. Okay, this is my Y bus. Now you can eliminate it. Now you can, let's say you want to find this Y11 new. So Y11 new will be equal to Y11 old, that is minus J4.5 minus, tell me guys, minus Y1 and Y13. 13 is J2. 13 is J2, Y13 into Y31, this is again J2, divided by minus J14. Okay, this will be my Y11 new. Okay, the new Y11 you'll get. Is it fine, guys? So you have to be careful while eliminating the node. If the node, the zero node is, I mean the node which has zero entering current is already at the lower position, at the lowest position, then no need to switch row and column. Okay, but if the zero entering current node, zero entering current bus is in between, let's say in this question you can see that at bus number 2 there is zero entering current. If there is zero entering current at bus number 2, then what you need to do is, tell me guys, what you need, at the bus number 2 there is no entering current. If there is no entering current at bus number 2, you can eliminate it. But this is in between, nah? This is not at the lowest position. That's why you have to switch it with the row number 3. Since you are replacing, you are interchanging row 2 and 3, you have to, you also have to replace column number 2 and 3. Okay, then only you'll get the correct answer. Otherwise, answer will not be the correct. Okay, I hope you understood it. Is it fine, guys? Tell me, have you understood it? So let me contact to Ashutosh sir, and I think Ashutosh sir will carry on from this point. And there will be some point about Z bus also. I want to tell you about the Z bus also and how to formulate this Z bus. But I will take some other session, and in that session I will discuss how to formulate Y bus and Z bus, and what is the meaning of Z bus and how to calculate the fault current. Okay, because 2 hours are not enough actually. If I want to teach you about some point, or if I want you to understand something, then obviously 2 hours are not enough. Okay, but anyway, you have to understand this concept, how to do this, how to eliminate the row in the Y bus. Okay, and the per unit system I told you, because this is again very important, because many students do mistakes in this per unit. Okay, so be careful guys, don't do mistakes. So let's stop it here, and let me contact Ashutosh sir so that he can join and he can continue from this point onward. Okay, so wait a minute guys. Hello guys, so sir will join maybe after 10 minutes. Okay, so till then I can continue with the class. Okay, so I told you how to eliminate this, the Y bus, and how to find the new Y bus. Okay, 2 by 2 matrix. There is one more method. What you can do is, you can make this star in delta. If you convert this star in delta, then the circuit will look like this. If you can make this star in delta, then it will be like this. Is it fine? If you can make this star into delta, it will be like this. And here there is one more. Is it fine guys? Okay, so now you can see that if I make the star into delta, this is my delta, only 2 buses are there, bus number 1 and bus number 3. Is it fine? Now you can calculate y11 new. You can also calculate y11 new via this method. Via this method you can also calculate y11 new. So the y11 new will be 1 by this value plus 1 by this value plus 1 by this value. So we need to calculate this value and this value. Now how to calculate this value and this value? Because you are applying star delta conversion. This is my star, you can see that this is my star. I need to convert the delta. So let's calculate this value first. And let's see whether you have done via this method, is it correct or not? I mean, what is the answer from this method and what is the answer from this method? Let's see whether you are getting the same answer or not. Okay. So how to check it? What I have done is I have converted this star into delta. This is my delta. This is pi network. Now, what is this value? First of all, I have to calculate this value. How to calculate this value, guys? It will be j.5 plus j.5 plus this into this, that is j.5 into j.5 divide by this reactance j.1. Okay, this j will cancel and it will become j1. It will become j1 plus j. This is j1 plus j into 2.5. Is it fine, guys? So it will become j3.5. Fine. Please check it. So it is j1 and this will become 5. 5 into 0.5 is 2.5. So it will be j2.5. So now the resultant is j3.5. So this has to be j3.5. Now what is this reactance? What is this reactance? The reactance between this and this. Tell me, guys, this and this ground. So it will be j.5 plus j.1 plus j.5 into 0.1 divide by the third j.5. Fine. So you can cancel it. So it will be j.7, j.5 plus j.1 plus j.1. So it will be j.7. So this will be j.7. And this value is already provided to us as j.4. Okay. Now what you can do is you can calculate y11. So the y11 new will be equal to 1 upon this plus 1 upon this plus 1 upon this. So 1 upon j 0.4 plus 1 upon j 0.7 plus 1 upon j 3.5. Okay. So this way you can calculate y11 new. 1 upon j 0.4 plus 1 upon j 0.7 plus 1 upon j 3.5. This way you can calculate the y11 new. So if you calculate this value, it will be, let me calculate it, 1 divided by 0.4 plus 1 divided by 0.7 plus 1 divided by 3.5. If you calculate this, it will be 4.21 minus j 4.21. This will be my y11 new using star delta conversion. I hope the calculation is correct. Okay, I hope the calculation is correct. So we have eliminated bus number 2. If you have eliminated the bus number 2, then this star will become in delta. This star will become in delta. Now you can see that there is only 2 buses, bus number 1 and bus number 3. So you can calculate y11. Y11 will be 1 upon this plus 1 upon this plus 1 upon this. Okay, we have calculated y11. Now we did the same thing by node elimination. We have calculated the y bus for 3 bus system, and then since the bus number 2, at bus number 2 there is no entering current, so we can eliminate the bus number 2. How to eliminate? What you can do is first you interchange bus number 2 with bus number 3. So you interchange them. Not only the bus number 2 and bus number 3 are interchanged, I mean the row number 2 and row number 3 are interchanged, you have to interchange the column also. Column number 2 and column 3 should also be interchanged. Now this is my y bus and this is my second bus. Now this is the lowest bus I have. I need to eliminate them. I need to calculate this y11 new. So y11 new is y11 old minus y13 into y31 divided by this value. Okay, let me calculate this value so that I can get the answer. So this is cancelled here and this becomes 7. Okay, and this minus minus will become plus. Is it fine, guys? So it will be minus j 4.5 plus j 2 by 7 plus j 2 by 7. If you calculate this value, tell me what is this value, guys? Tell me. So it will be minus 4.5 plus 2 by 7. It came out to be 4.21 minus j 4.21. You will get this value. Now what is the value that we have previously got? Minus j 4.21. We get the same value. Okay. So you can do the same. You can do the problem like this. But this is not a good method. Why? Why I am avoiding this method? Why I am not interested in this star delta conversion? Because this is valid whenever you see the star only. If there is no star point, what will you do? Okay. Then you have to go with this method, na? That's why I am telling you. Okay. That's why I am telling you. So be careful, guys. Be careful. You have to be, whenever you look at this star, luckily in this question we have this star point. So if there is a star point, you can eliminate that. You can eliminate, this node you can eliminate via star delta conversion. And then you can calculate y11. No problem at all. Okay. But you should know how to eliminate the same bus number 2 using this method, using this node elimination method. I hope it is clear. Now let's come to the new thing, that is Z bus. How to calculate Z bus? How to calculate Z bus? Z bus can be calculated by taking the inverse of the Y bus. Remember this point. Okay, how to calculate Z bus? Z bus can be calculated by taking the inverse of the Y bus. If you know the Y bus, you take the inverse of that, you will get the Z bus. But there are some students who think that, sir, you calculated Y bus using the nodal analysis. Using the nodal, you have written the node equation, V1, V2, V3. And this is the coefficient of V1, this is the coefficient of V2, this is the coefficient of V3 equal to the entering current. So this is the byproduct of nodal equation. Okay. From the nodal equation, we have written this equation. So the coefficient of voltage is Y bus in nodal equation. You can write the nodal equation at this V1, V2, V3. You can write the nodal equation for 3 variable, and then you can find this equation directly. Okay. Now many students think that, okay, Y bus came from the nodal, so Z bus will come from mesh. Answer is no. Z bus will not be the byproduct of mesh. Okay, you can't get Z bus from mesh analysis. For Z bus, you have to take either the inverse of the Y bus, or there are some other methods to calculate Z bus. What are those methods? Let's say we have a 3-bus system. We have a 3-bus system. In 3-bus system, obviously there will be 3 junction voltages, V1, V2, V3, 3 bus voltages, V1, V2, V3, and there will be entering current I1, I2, I3. These are the entering current I1, I2, I3. How to calculate these entering current? The entering currents are these currents. You can convert these voltage sources into current sources, and they will become entering current. Is it fine? So entering current is at this junction entering current is I1, at this junction entering current is I2, at this junction entering current is I3. Okay, so I call the I1, I2, I3 as the entering current. Okay. Now what you can do is, you can calculate the single element. The single element you can calculate. How to calculate this single element? Let's say you want to calculate Z22. Let's say you want to calculate Z22. How to calculate Z22? What is the meaning of Z22? What you can do is, to calculate Z22, make I1 equal to 0 and I3 equal to 0. It means there is no entering current in bus number 1 and bus number 3. There is no entering current. So the original circuit was like this. Original circuit was like this. Let me write the original circuit. So this was the original circuit, guys. The original circuit was like this. This was the original circuit. Now what you can do is, first you have to eliminate I1 and I3. There should not be any entering current at bus number 1 and bus number 3. So for that you can deactivate this source, because of this source entering current is there, na? So what you can do is, you can eliminate these sources. You can deactivate these sources, sort them. Okay, so you can sort these sources. Once you sort these sources, then try to enter some current I2 here. Try to enter this current I2 here. Okay, you sort them, this source is sorted, this source is sorted, and then try to enter the current I2 here and calculate the voltage V2. Calculate this voltage V2. The voltage across this current source, you calculate this voltage V2. Okay, you have to eliminate this source and this source and try to enter the current I2 here. I2 you can take any value. Let's say I2 is 1 ampere I have taken. And try to calculate this voltage. This voltage divided by this current value will be Z22. Okay, this will be Z22. Now if you look at this carefully, this is the Z Thevenin at this junction. This is the Thevenin impedance at this junction. How to calculate the Thevenin impedance? If you remember, let's say you have a circuit. And you want to calculate the Thevenin impedance of this circuit. What you need to do is you need to apply some current source of 1 ampere value and try to calculate the voltage across this current source. That voltage divided by that current will be the ZTH. You are doing the same thing. You have deactivated the source first. You have deactivated the source so that there is no entering current at the junction number 1 and junction number 3. So there is no entering current now. At junction 1 and 3 there is no entering current. Now what you did is you have entered some current I2. Let's take I2 as 1 ampere. So you have entered current 1 ampere here and you calculated the voltage across this current source. Voltage across this current source is V2 itself. You have calculated the voltage across V2. Okay. So V2 divided by this 1 will be Z22. So Z22 is the Thevenin impedance at bus number 2. Similarly, Z33 is the Thevenin impedance from bus number 3. You can calculate the Thevenin impedance at bus number 3, that we call Z33, and Z11. What is Z11, guys? Z11 is the Thevenin impedance seen from bus number 1. Okay. So you can calculate Z11, Z22 and Z33 directly if you know the Thevenin method. So using the Thevenin method, you can calculate Z11, Z22 and Z33 directly. Okay. I told you how. And what is the meaning of Z11, what is the meaning of Z22 and what is the meaning of Z33. I hope it is clear to everyone. Okay. So maybe in the next session, whatever the next session will be, in the next session, I'll tell you how to calculate these other Z parameters. Okay. I mean, the same way you can calculate the other parameter. You have entered I2 here, calculate this V2 and then calculate the V1 also and then calculate the V3 also. So take V3 upon I2. V3 upon I2 is this Z32 and V1 upon I2 is Z12. Okay. This way you can calculate the impedances, the Z bus values, the Z21 and Z22 and Z23. Okay. These values you can calculate. I hope it is clear to everyone. Not these values. These values will be appear, na? Because I1 you have taken 0, I3 you have taken 0. So only V1 will be equal to Z12 into I2. V2 will be equal to Z22 into I2 and V3 will be Z32 into I2. So take this I2 in the denominator. So V1 upon I2 is Z12. Okay. Similarly, V2 upon I2 is Z22 and V3 upon I2 is Z32. Okay. So you have to eliminate these sources and enter the current I2, calculate V2, V3 and V1 and take this ratio. Okay, you will get these three parameters. Similarly, you can calculate these 3 parameters and you can calculate these 3 parameters. This way you can calculate the Z bus. There is one more method for Z bus and that method is this modification. Okay, there is some modification method and I will take this session, maybe take this modification method in some other class. Okay, but let me talk to Ashutosh sir whether he is available or not. If he is available, then I have to from now on Ashutosh sir will take the class. If he is not available, then I will continue. Okay, so let me talk to sir.
So hello friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers, all the candidates who are live with me. Just quickly confirm once whether my audio visual quality, everything is clear so that we can start with the session. So I think audio and visual quality, everything is clear. So I hope you must be enjoying the concepts given by Ashu Jhangra sir. I'm fine, Raghu. Good evening everybody, welcome to the session. So we have to do a lot of topics now, a lot of topics remaining that I have to take care of. So we'll see how much we can complete today, and if it requires, then we'll plan one more session for power system, because topics are quite good in number and that we have to complete. And because it's a promise that we'll be giving you the complete coverage of the syllabus for your revision for upcoming GATE examination, so definitely we'll complete it. So everybody, just once again stay connected. I will give you some information and then we are going to proceed. Some of you may be joining me for the first time, so there is a brief introduction about myself. My name is Ashutosh. As you can see on the screen, I have 11 plus years of teaching experience. I'm from ITBHU in 2010. I have written a couple of books and these are my areas of expertise. All the candidates, just quickly hit the like button, hit the bell icon and subscribe to BYJU'S Exam Prep if you have not subscribed, so that you do not miss any of the important session. So congratulations, admit cards are out and I hope one day you will be getting your scorecards also one day. So you must be aware that right now we are in Maha Marathon series, daily 10 a.m., 4 p.m. in the evening. You are getting one of the best quality content revision for your upcoming GATE 2023 examination. Within just 12 days, all your subjects are going to be completely revised for electrical, electronics, instrumentation and computer science. 15th of January, everybody's favorite, my favorite, Abhinav Negi sir is going to take a mega workshop on 7 success mantras from a beginner to a topper in GATE 2024. So if you have a junior, if you have a colleague, so do some kind of samaj seva. दूसरों की सेवा करोगे तो मेवा मिलेगी. And attend this session. You have to get yourself registered. It is going to be conducted 15th of January, 12:30 p.m. Now, once again, the legendary faculty for aptitude and mathematics, Rakesh Talija sir, is bringing 15 marks in just 15 hours. Complete general aptitude he is going to cover very soon. So stay connected. Rakesh sir and Ankit Joshi sir, two legendary faculties for mathematics, they are coming with Nothing is Impossible 2-day session, non-stop maths marathon session, where the complete mathematics is going to be revised. This is about the GATE and Engineering Services test series, where you will be getting full-length mock subject test. The link is given in the description. What are the important features for this test series? You will be getting 60 plus tests covering GATE and Engineering Services, detailed mock analysis, virtual scientific calculator, 4,000 plus practice questions, all India open mocks. And all these test series are being curated by the best experts in the GATE or engineering services. So yesterday we were about to start the HVDC transmission. So I will be starting from HVDC transmission. Let me just list out what are the topics we have to cover. So today first we will be having HVDC transmission. Then I will be talking about power distribution. Then we'll be talking about stability. Then I will be talking about circuit breaker. Then I will be talking about relays. So the only topic that is remaining here is fault. So let us see how much we can complete today, and that what is remaining I am going to club with faults, and we'll have another session maybe after 2-3 days, and then we'll be having the complete coverage for the syllabus. Let us start with the HVDC transmission. Yesterday when we started with this, I told you that if you talk about the generation, we don't go for DC when it is about generation, because DC generators at this much power level is going to be quite uneconomical because of the commutation problem, and it is going to be quite difficult to provide effective cooling at this power level. So we go for generation, we go for AC. Also, you cannot generate reactive power, and reactive power is required in your system. So better we go for the synchronous generators only. If you talk about the load or the final power consumption, this is also in AC, because suddenly you cannot say that no more AC loads are not allowed and only you have to go for DC loads, because it is a very complex system and one single day it cannot be changed. It means for power generation and load consumption, we have to go with the AC. Okay. Now there is only one portion remaining, that is transmission and distribution, where you can use DC. Now we started with DC. Okay, actually we started with DC when we talked about electrical power, but suddenly now why we are talking about HVDC, so we'll understand what are the reasons, what is the significance why we go for HVDC. The basic idea about HVDC is you have converter stations both at the sending end and the receiving end. At the sending end, the converter station is going to behave as a rectifier, so it converts AC to DC. At the receiving end, the converter station is going to behave as the inverter, and it is going to convert again DC into AC. So both the load side and the generator side you have AC, whereas in between you have HVDC transmission. What are the important advantages of having HVDC transmission? Let us understand. HVDC is more effective beyond a certain distance for transmission, that we will discuss. That up to a critical distance, approximately 500 to 600 or 700 kilometers, you can say HVAC is preferred. But beyond that critical distance, HVAC is not preferred, HVDC is preferred. Why? We will understand. Second, HVDC facilitates the interconnection between two asynchronous systems. What do you mean by two asynchronous systems? Suppose there is system 1 operating at 50 Hz and system 2 operating at 60 Hz. HVAC will not allow connecting these two systems by using HVAC line or HVAC link. In order to connect these two asynchronous systems, you require, it is HVDC, because HVDC is basically asynchronous link. Yes or no? It is going to be an asynchronous link. So two systems operating at two different frequencies can be connected, and there can be exchange of power if you have the HVDC link or connection. HVDC has the most important advantage as HVDC back-to-back connection. What is HVDC back-to-back connection? When the rectification and the inversion, both the operations are done at the same time, at the same place, then we call that system as HVDC back-to-back connection. Here you have AC system, here you have AC system. Now you have a transformer. The secondary of this transformer is applied to the rectifier circuit. Now rectification and inverter operation both are done at the same time, so it works as HVDC back-to-back connection. The basic idea of this HVDC back-to-back connection is that two different frequency regions or two power systems operating at two different frequencies can be connected together, so that exchange of power can be facilitated. For metropolitan cities, and if we are talking about metro cities, smart cities, we can go for HVDC cables. HVDC cables have a lot of, now because देखो तुम्हारे जैसे बच्चों की वजह से ही अच्छे टीचर जो है आजकल सुसाइड कर रहे हैं. Before you ask me this question, you should have gone to the syllabus. Okay, HVDC is in the syllabus. ठीक है, ऐसे क्वेश्चन नहीं पूछते बाबा. ठीक है, चलो कोई बात नहीं. Yes, so HVDC cables we can use instead of HVAC cables, because HVAC cables have limitations in terms of charging current, so they are not being used beyond 50 kilometers. But no, don't say, sorry, I was just joking. Okay, take it lightly. I was just joking. So because of the charging current and various other reasons, we don't go beyond 50 kilometers when we are talking about HVAC cables. So we can go to HVDC cables where these issues are not there. Radio interference is not there. Charging current is not there. So because of these advantages, ideally you can go up to any length when you talk about HVDC cables. Okay. Now, if you talk about the HVDC in comparison to HVAC, now you tell me, if you talk about AC system at the sending end and the receiving end, you just require transformers, yes or no? The main component is going to be transformer, apart from other protection devices, maybe circuit breaker and relays, that is going to be present in DC also and AC also. That does not make a difference. But in case of AC systems, transformers are the main component. At the generator side, step up transformers are used, and at the load side, step down transformers are used. But when you talk about HVDC, it's not just the transformer, there are so many other equipments. The whole converter station is there, filters are there, rectification and inversion circuits are there. Okay, reactive power support is required, because whenever power electronic devices are included, there will be some reactive power requirement. Smoothing reactors are there. Okay, and yes, so all these devices, they comprise the complete converter station for HVDC. So that is why we say the terminal cost of HVDC is high. Terminal cost means at the starting or the end, or you can say at the sending end or the receiving end, the terminal cost of HVDC is going to be high, but the running cost of HVAC is high, because HVAC you are using 3 conductors for 3 phases, whereas if you see, if you have HVAC, it is going to have 3 conductors, 3 phase. But if you talk about HVDC, simply if you have a bipolar HVDC connection, that is going to have the same amount of power transfer capability as that of your HVAC system. So definitely when more conductor is used, more losses will be there. It means the running cost of HVAC is going to be higher in comparison to HVDC. So this thing is clear for everybody. Terminal cost of HVDC is high, whereas running cost of HVAC is high. This you can understand by this diagram also. This is the distance traveled over the length of the transmission line, and this is the overall cost. So if you see at the sending end, when length is 0, you can understand the terminal cost of HVAC is less, because the major component is protection and transformer, whereas the terminal cost of HVDC is going to be at a higher side, because the whole converter station you require if you want to go for HVDC. But after certain critical distance, I take it around 500 to 700, okay, critical distance, you can see the running cost of HVAC becomes very high in comparison to the running cost of HVDC. So less than up to 500-600 kilometers, we are going to prefer the HVAC transmission, whereas beyond this we prefer HVDC transmission. And theoretically, if you ask me, theoretically there is no limitation in terms of the length of the transmission line if you are going for HVDC. So for very, very long distances, if you want to transfer the power, HVDC is going to be the best choice. DC does not have any stability issue in terms of angular stability. Yes or no? In HVAC, you have a stability issue. So beyond 500, we do not go for HVAC. HVDC has less corona. One reason is the frequency is 0. Yes or no? So you know that corona loss is directly proportional to F plus 25. If you remember the peaks formula. So when frequency is 0 for DC, you can understand the corona is going to be less. Corona loss is going to be less for HVDC. There is one more reason. If you talk about HVDC, suppose you have only one conductor for HVDC, and it has the positive polarity. Sorry, it has the negative polarity. The conductor polarity is negative, because in DC you can have only positive polarity and negative polarity. Yes or no? It's not changing with respect to time. It's constant. Now, if the conductor is at the negative potential, negative polarity is there, then the free electrons near the surface of the conductor are going to be repelled away. Yes or no? Why corona was happening? Corona was happening because of the excess electrons near the surface of the conductor. How many people are comfortable with the corona phenomena? Just tell me in the comment section. Everybody is comfortable? If not, I can give you some idea. Yes, everybody. Tell me fast. Everybody is comfortable with corona phenomena? Yes. This year you may be getting a question on this. That is why I am saying. Everybody is okay with that? Okay. Charging current is not present. Why? Because charging current is present because of the time varying electric field. Now when you deal with DC, there is no time varying electric field, so there is no charging current present. Skin effect and proximity effect are also not present because skin effect and proximity effect, they also depend upon the time varying field, and that is the reason for DC systems skin effect and proximity effect is also not present. Everybody is comfortable with skin effect and proximity effect? Just tell me short, tell me fast. Skin effect, proximity effect, okay. Now, except the converter station, there is no reactive power requirement for the HVDC transmission. Now, if you observe the HVDC system, suppose this is the HVDC system you have. So, wherever you have power electronic devices, that is at the converter station, you require some reactive power support. But in between these two converter stations, that is throughout the HVDC link, there is no requirement of reactive power compensation. Whereas if you go for the AC system, HVAC systems, you require reactive power support to maintain the voltage at the receiving end and to improve the power factor. Yes or no? Next, better control facilities due to the, it's not poorer, it is power electronic devices. So you know that power electronic devices are very fast switches which can operate at power frequency, which can operate at high power. So you have better control facilities in case of HVDC. Switching transients are not present because you are dealing with DC. That is the one reason, and another reason is you have fast switches. That is why transients are not present. Fault clearing is also fast. Why fault clearing is fault? This is important to understand. If you talk about the HVAC systems, let me just introduce one extra page here so that you can understand it better. So everybody just take very much care of your health, because I can tell you right now the next 15 days are very crucial for you. And right now the weather is such that almost every second person is getting some cold, cough and something. I also got a lot of cold and cough yesterday. Okay. So be very careful, because it is going to waste a lot of your time, energy, motivation. So be very cautious about your health. Follow what your parents are saying. If you talk about HVAC, in HVAC systems, what happens? Suppose you have a network like this. Suppose this is bus number 1, this is bus number 2, this is bus number 3, and there can be some other buses or network present in your system. Okay. Now suppose if there is any problem, any fault or anything occurring at bus number 2. Okay. So the changes at bus number 2 are dominantly seen at those buses which are directly connected to this bus only. Generally not to the other part of the system, other buses in the system in case of HVAC. But when you talk about HVDC, in case of HVDC, if one bus has some changes with any respect, then it is spread all across the system, and that is the reason when we are talking about HVDC, we have faster circuit breaker and relays, so that the fault clearing time is going to be less in case of HVDC. Is it clear, everybody? Previously there was a question on this concept, so I thought better to explain it. Now let us see the types of HVDC link that you can have. You must be having some idea. I'm just going to give you a quick revision. There is a monopolar. Mono, the word itself tells you only one conductor. So only one conductor is there. There is a transformer. Secondary of the transformer is connected to the rectifier, and at the receiving end, another converter station you have that operate as an inverter and connected to the another transformer. Now this is at the negative polarity. This is at the negative polarity. Why negative polarity? Because of negative polarity, the free electrons present here, they are repelled away. When the free electrons are repelled away, the possibility or the intensity of corona is going to be quite less. But it has less power reliability. Why? Because it has less corona also. Why less power reliability? Because only one conductor is present. So if there is any damage, any repair, then you cannot transfer the power at all. Second, we have the bipolar HVDC link. As the name indicates, it's going to have two conductors. Now one conductor is going to be at the positive polarity and another conductor is going to be at the negative polarity. But what we are doing, we are grounding the midpoint. Why we are grounding the midpoint? It saves the insulation basically. It is a very famous classical question in interviews. Because what happens with this reference, this is going to be VD by 2 and this is going to be VD by 2. The total becomes the same as VD, but because you have taken the midpoint earthing, that is why the insulation is being provided against VD by 2, not VD, and that is a saving in the insulation. Okay, so you have two conductors now, one positive, one negative. So power reliability is going to be increased. Power reliability is going to be increased. Now if you see, if the current is going from sending end to receiving end like this and receiving end to sending end like this, then the current which is flowing here in the ground or the earth is going to be 0. If the current flowing in the ground or the earth is going to be 0, it means there is no radio interference with nearby telecommunication channels. Okay, underground cables. This is underground cables. But if you talk about this monopolar HVDC link, only one conductor is present. So definitely the ground has to act as a return path. When ground has to act as a return path, then definitely the radio interference is present. Radio interference is present. The third one we have is the homopolar HVDC link. As the name indicates, homopolar HVDC link is going to have again two conductors, both at the negative polarity. Both at the negative polarity. So current is coming in this direction, so definitely current going through ground is not 0, and that is why radio interference is going to be very high in this case. But corona is less and power reliability is better because you have two conductors. Is it clear, everybody? Now let us talk about the HVDC converter station. Why the numbers are getting down? मजा नहीं आ रहा है? थोड़ी बहुत हिंदी भी यूज कर सकते हैं क्या? Can I use a little bit of Hindi? You're not getting interest. बहुत सिंपल चीजें हैं. So stay connected. We are going to discuss after this power distribution. Okay, so do not lose your concentration. I am going to discuss each and everything in your syllabus, each and everything in your syllabus. So if you miss this opportunity, and most of you, if you are thinking that you can make it up if you see the recorded video, that is not going to help you. Okay, it is always better that you see the session live. That is much better. Anyways, now let us discuss about the HVDC converter station. So I will discuss some of the components of HVDC converter station because single line questions can be asked here. So first you have this HVAC bus. Okay, this is AC, high voltage AC transmission bus is there. Now you have transformers, and the transformer secondaries are connected to the rectifier circuit. You see here, rectifier circuits. After the rectifier, the output, you have a smoothing reactor, and there are some DC side filters also. These are DC side filters and these are AC side filters, and you have some reactive power support also. Is it clear? So beyond this also you have the DC line like this. Now one important point which is very frequently asked in various interviews also and examination also, you see here, instead of using one rectifier circuit, we are using two rectifier circuit here, if you observe properly. Yes or no? One rectifier circuit, two rectifier circuit. We are using two set of transformers. One is star star, one is star delta. Why? What is the reason? What is the reason? Understand the reason. What intelligent thing, smart thing we are going to do is, if you have only just one rectifier, if you have just only one rectifier circuit, what is happening? What output you are getting is going to have lot of ripples like this. Suppose you are having a 6 pulse converter. 1, 2, 3, 4, 5 and 6. Suppose you have a 6 pulse converter. So lot of ripples, lot of disturbance is going to be at the output of the converter, which you don't want, because you want almost as much pure as you can get, that much pure DC you want. So what we are going to do is, by using this star star and star delta transformer connection, we are going to add these two rectifiers in series and giving a 30-degree phase displacement. And then this VD1, VD2 is going to be added. So if you see how ripples are going to be reduced, suppose this is VD1, okay, 6 pulse. This is VD2 given a 30-degree displacement by using a star delta transformer connection. So this 6 pulses are shifted like this. Now because they are connected in series, so the final rectifier output is going to be VD1 plus VD2. Okay, VD1 plus VD2. So if you add it up, the ripples are going to be smoothened. So this is a 12 pulse DC output. So more number of pulses means what? Ripples are going to be improved. More number of pulses means what? Ripples are going to be improved, and that is the reason instead of using one rectifier, you are using two rectifiers with two transformer connections, star star, star delta. I hope it is clear. Now let us talk about the three-phase bridge rectifier, full wave rectifier, GATE circuit. You may get a question on this. So the equivalent circuit, including the effect of commutation, what you are getting is, the equation that you are getting is VD is equal to V naught cos alpha minus, this is the rectifier output current ID, it is 3x upon pi, and this is ID. The only thing you have to remember in this equation is this circuit and this equation. This is the actual output. This is the actual output of your three-phase full wave rectifier. What is this V naught? This V naught is 3 root 3 Vm upon pi. This V naught is 3 root 3 Vm upon pi. You must have read it in your power electronics. Alpha is the firing angle. Now X is the reactance, but this 3x upon pi, it actually behaves as a fictitious resistance. It behaves as a fictitious resistance. But there are no actual losses because it is not a resistance actually, it is a reactance. It is just for the sake of giving you the equivalent circuit. Now if you see the question, this question you cannot solve if you don't have this equation. Just try to solve this question. What he is giving you as information, let us see. A bridge rectifier delivers 800 ampere current. So the output rectifier current is given as 800 ampere. When rectifier output is 100 kilovolt, rectifier output is, final output is given as 100 kilovolt. Transformer secondary tapping is given. Transformer secondary tapping is given. The transformer rating is also given 220/110 kV. The firing angle alpha is given as 30 degree. He is asking find the effective reactance per phase. Now please understand, what was the equation? The equation was VD is equal to V naught cos alpha minus 3x upon pi, and this was ID. In this equation you just need to put the values. What is VD? It is given as 100 kV. What is V naught? V naught you have to find separately. V naught is 3 root 3 Vm upon pi. This is 3, this is root 3. What is Vm? Now please understand what is this Vm. Always you are connecting the secondary of the transformer to the rectifier. Yes or no? Secondary of the transformer you are connecting to the rectifier. So we are going to deal with the secondary voltage of the transformer. The secondary voltage of the transformer is given as 110 kilovolts. 110 kilovolts. But there is a tapping of 0.85, 85%. So multiply by 0.85, because tapping is there. Only 0.85% of the total secondary voltage is coming across. But my friend, you have to write here, what is this? This is peak, this voltage is per phase peak voltage. Yes or no? It is per phase peak voltage. So when you have this 110 kilovolt as the rated secondary, this is actually line RMS voltage. Line RMS voltage. You have to change it to the per phase and the peak value. So first change it to the per phase, so divided by root 3. Yes or no? And you have to multiply it by under root 2 to make it peak value. Yes or no? Are you able to follow this? Are you able to follow this or not? Just put all these values. The only thing unknown is X. You can find X. This type of question this year you can get in HVDC. Okay. And this is extremely important. I am going to give it 7 stars. Twinkle, twinkle, little star. If you want more explanation, I can give you more explanation. I can do it again if you have any problem in this. This equation you have to remember. This circuit, equivalent circuit for 3-phase full wave bridge rectifier. Great circuit you have to remember. And you understand how you are writing V naught. Okay. I hope it is clear. Now if you talk about the AC filters. AC side filters, the order of harmonics is given as NP plus minus 1 where N is 1, 2, 3, 4 and P is the number of pulses. Okay, number of pulses. So for a 12 pulse converter, it is going to be 12 N plus minus 1. Just keep on putting different values of N and you will get the order of harmonics. Similarly, for DC side filters, the P pulse converter is going to have a harmonics of order N into P. So for a 6 pulse, you have 6, 12, 18, and for a 12 pulse, you have 12, 24, 36, so on. You may get a question on this. The important part is that both AC and DC side filters are going to be high pass filters and they are shunt filters. The filters at AC side contribute to some extent to the reactive power requirement at the converter station. So this is the end of HVDC. I hope you enjoyed it. Now we'll be talking about power distribution. Is it clear, everybody? Okay. Let me add one page here. So if you see your power distribution system, you can understand like this. So this is your transmission line. This is your transmission line. This is your distribution transformer. This is your distribution transformer. This is your feeder. This is feeder. And this is your distributor. Distributor. Now if you talk about some important points, you can note down. For the feeder, the current density is constant. Like you have for transmission line, current density is constant because load tappings are not allowed. Load cannot be directly connected to the feeder part. Now feeder, why the name is feeder, you understand it. This is a step down transformer. This is a step down transformer. A step down transformer means suddenly the voltage has been reduced several times. So current is going to be increased multiple times. So it's going to handle bulk amount of current. Bulk amount of current it is going to handle. And that is the reason its name is feeder, because it is going to feed the current to the loads finally. Now, this is your loads, but they are not directly connected. Okay. These are connected through service mains. Service mains. These loads are connected to the distributor with the help of service mains. Now, because it is going to carry bulk amount of current, definitely temperature rise is a big concern, and current carrying capability is the important criteria for designing it. Temperature rise and current carrying capability. If you talk about the distributor, obviously current density is not constant because the loads are connected. Every moment the loads are going to take some current, so current density is not constant. For designing the distributor, voltage drop is the main criteria. Voltage drop is the main criteria. Several times this question has been asked. So you must understand this. It's like the canals, okay? For irrigation purpose, you must have seen canals in villages, okay? So what happens? The first tunnel which is going to your village, the best of the regions are going to be the big landlords who are getting the water first. At the fag end of the canal or the tunnel, very marginalized small poor farmers are going to be getting the water. Now, as a power system engineer, it's your responsibility that you ensure that the last person, the last load connected at this point must be getting a satisfactory power, quality and frequency. For that purpose, voltage drop is going to be the main criteria for designing the distributor part. Is it clear, everybody? So this is your distribution transformer. Basically, we have two types of distribution. This is primary distribution. Primary distribution is generally given to some manufacturing unit, to some big institutions which are going to have a significant load connected at their end. So they are going to have a 11 kilovolt line. And we have secondary distribution also. Secondary distribution is about the small and the medium consumers. This is for 3-phase and this is for single phase, you can understand. So I think everybody can do this question now. What is the criteria for selection of the size of a distributor in a radial distribution system? Yes, everybody. Yes, voltage drop. Voltage drop is the correct answer. Okay. Let us talk about the distributor, that is DC distributor. So basically you have two types of distributors in terms of whether it is going to carry AC or DC. So AC distributor is also there, but most of the time you will see you are getting a question on DC distributor. The reason is within the span of examination time, you can solve the questions related to the DC distributor, but the questions related to AC distributors, they are little lengthy, and that is the reason you see most of the time they are asking question on DC distributor, not the AC distributor, but AC distributor is also going to be similar. So first we have radial distribution system. Radial distribution system can be fed from one end. You can see here it is getting power from one end only. So two things you must be prepared with. What is the location of minimum voltage and what is the value of minimum voltage? So what is the location of minimum voltage? The far end is going to be the location of minimum voltage, and you can calculate what is going to be this voltage if you know what is the current in different sections, different parts of the distributor. One more important point here, whenever you are going to write the KVL equation, you will always use the loop resistance. The loop resistance is going to be 2 times the resistance given per unit length of the distributor. Are you getting this or not? Be very clear. If nothing is written in the question and it is simply saying the resistance of the distributor is this much for this much length or per unit length of the distributor, always multiply it by 2, because you have to talk in terms of the loop resistance. Okay, so 2 times R into ohms per meter. Writing the KVL, you will always use the loop resistance. So you can see how I1, I2, I3, I4, I5 loads are connected here. Now you have radial distributor which is fed from both the ends. So both the ends you are getting the power supply. Now the location of minimum voltage you will be deciding by the criteria that point or node which is getting current from both the side is going to be the location of minimum voltage. Getting the current from both the sides is going to be the location of minimum voltage. Ring or loop distributor. Now please understand, in radial distributor there is no closed loop. That is how we define it. There is no closed loop. But if you talk about the ring or loop distributor, so at least one closed loop is there. At least one closed loop is there. Now you understand this. Ring or loop distributor is nothing but like a radial distributor which is fed from both the ends. Yes or no? It is fed from both the ends. You remove it from here and just supply it here with the same amount of voltage, it is going to be similar. Hello? Are you getting this or not? So how you are deciding the location of minimum voltage? Again, the node at which you are getting the current from both the sides is going to be the location of minimum voltage, and you can find it by using the KVL equation. The third one, you have the interconnected system. Interconnected system is a complex combination of both radial and ring main system. So you see there is a loop also and you have radial network also. It is a combination of both of them. Let us try to solve this question, everybody. You have to find the value of V minimum. It is fed from both the ends. So what you are going to do? First, see, the radial distribution system is fed from both the ends. Each conductor is designed to have a resistance. Now he is giving you resistance of the conductor. He is not giving you the loop resistance. So this 0.15, this is ohm for 300 meter. Okay. So the resistance is mentioned as 0.15 ohms for 300 meters. So the loop resistance is going to be 0.15 into 2 ohms per 300 meters, or you can say 0.3 ohms per 300 meters. Is it clear, everybody? Now what we are going to do, suppose this is I current coming from this side, okay, I current coming from this side. So I will be here. Now 20 ampere gone, the load connected is 20 ampere. So it is I minus 20. This is I minus 20. When we start the analysis, we don't know what is the actual direction of current in different sections of the distributor. So what we do, you can assume any random direction as per your choice. You apply the KVL, and in any section if you are getting a negative current, just change the direction, magnitude will be same. Okay. So we are assuming this direction. Suppose this direction, this direction. So I minus 20 here, again 60 gone. So I minus 20 minus 60, I minus 80 in this section. Again 40 gone. So 80 minus 40 is minus 120. So it is I minus 120 in this section. Now, this V1, V2 both are given as 230 volts. This is also 230 volts. This is also 230 volts. So the total voltage drop in this distributor must be 0. So can you write the KVL equation with me? Can you write the KVL equation with me? Let me add some pages here. Now you see, the first thing you have to do is you have to write the resistances for the different sections. Section 1 is 50 meters, section 2 is 100 meters, section 3 is 50 meters, section 4 is 100 meters. So you can say R1 and R3 are going to be same, R2 and R4 are going to be same. So R1 and R3 I am writing, it is going to be 0.3 for 300 meters. And what is the length of R1 and R3 sections? It is 50 meters. Can you solve it for me? R2 and R4 are going to be same, 0.3 for 300 meters multiplied by, because R2 and R4 have 100 meters length, so it is 100 meter. So what is the value you are getting? Just tell me. I think you must be getting it 0.05 ohms, and this you must be getting as 0.1 ohms. Yes or no? Yes, Krishna. Perfect. Now I am going to write the KVL equation here. So I multiplied by R1, I multiplied by R1 plus I minus 20 multiplied by R2, I minus 20 multiplied by R2 plus I minus 80 multiplied by R3, I minus 80 multiplied by R3 plus I minus 120 multiplied by R4. This must be equal to 0. Now you understand, we know that R2 and R4 are 2 times of the R1 and R3. Yes or no? Yes or no? So R1, R3 I am writing as 1 and R2, R4 I am writing as 2. Can I write it? Now you simplify. So it is I, 2I, 3I and 3 and 2, 5I is equal to, this is 40, 80, 120, 120 and 240, 360. Something wrong I have done, let me check. I, 2I, 3I, 4I, 6I. Okay, it is 6I. This is 6I. So what is the value of I you are getting? I you are getting as 60 amperes. Now just put the value back. Put the value back. Now here it is going to be 60 amperes. Here I minus 20, so 60 minus 20 is 40 amperes. This is I minus 80, 60 minus 80 is minus 20. The moment you get minus 20, the magnitude remains same, the direction is reversed. Direction is reversed. So this is going to be 20 ampere. This is I minus 120. 60 minus 120 is minus 60. Minus 60 means what? Direction change, magnitude same. So this is 60 amperes. Now what is the location of minimum voltage? This is going to be the location of minimum voltage because current is coming from both the sides. Current is coming from both the sides. Can you tell me what is the value of this V minimum? Yes, V minimum is going to be this voltage minus this drop and this drop. So it's a very easy question now. V minimum becomes V1 minus. Now directly you can write what is V1. V1 is given as 230 volts. So 230 minus I into R1. What is I? 60. What is R1? 0.05 minus. Second section, what is the current? 40. 40 into R2 minus 40. What is R2? 0.1. Just solve this. This is 230. Okay. This is 3. This is 4. So this is 223 volts. Are you getting this? Everybody just tell me in the comment section. Fast. And can you share the session with your friends and colleagues? Very less number of students. It should be minimum 1500 students. Okay. So can you share it once with your friends and colleagues? Is it clear everybody? जैसे ही मैंने कहा कि भैया शेयर कर दो, एक बच्चा और कम हो गया. वो लग रहा है वो मैनुअली शेयर करने चला गया है. ठीक है, सही है. मुझे कोई दिक्कत नहीं है. मुझे तो टॉप 10 में 10 बच्चे चाहिए ना. अगर 12 बच्चे 15 बच्चे हैं तो मेरा तो काम हो गया. मुझे तो टॉप 10 में तो 10 ही बच्चे चाहिए ना. ज़्यादा से ज़्यादा 1-2 की रैंक सेम हो जाएगी. ओके. So everybody got the question? Now let us talk about this uniformly distributed DC distribution system. It is my gut feeling that 2023, I am going to give it 7 star because highly possible that you will get a question from this. Number of times they have asked from DC distributor in general. Now this is the time you may get a question on uniformly distributed DC distributor. What is the whole idea of this uniformly distributed DC distribution system? Let us understand. In general, if you see the distributor, okay, what happens, suppose this is your distributor, okay. Now actually if you observe it in a practical world, the loads are not connected like this, that one load is here, 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 and one load is here. Actually in practical system, the number of loads is going to be very high, so the load density is going to be very high. So in the real system, it is something like this. In the real system, it is something like this. So it is very difficult to represent the load. So what we are doing, just see here. Instead of defining I1, I2, I3, I4, I am simply designing the load as I ampere per meter on the distributor. I ampere per meter. The resistance I am defining as R ohms per meter. This highly dense load is represented like this. This is the uniformly distributed load. This is I ampere per meter, okay. And this is the resistance, okay, R ohm per meter. Number of loads are very high, so load density is also very high. Now suppose I want to know what is the total voltage drop in this distributor. What is the total voltage drop in this distributor? So I am not going to the derivation part, I am directly giving you if you want to write the voltage drop for X distance, then it is I into R. Because generally how you are writing the voltage drop, current multiplied by the resistance. Now current and resistance both are given in per unit, so you have to multiply it by distance. Which distance? X. So it is X square. And what is the power of X? You divide it by that. So this is going to be your expression for the voltage drop for a distributor having a length X. Now suppose you are trying to find what is the total voltage drop here. So what is going to be the total voltage drop? Then X becomes L. So delta V X, sorry, this delta V for a length L is going to become as I into R into L square by 2. Is it clear, everybody? If you want, then you can rewrite it. You can write this voltage drop as small I into L, small r into L divided by 2. So it becomes capital I into capital R by 2. And this is very interesting result. Generally, you have the voltage drop as I into R. But in case of uniformly distributed DC distributor, it is going to be capital I into R by 2, where capital I is the total current, that is I, total load, that is I multiplied by length L, and R is, capital R is the total resistance of the distributor, that is small r into L. Everybody is okay with this? Any doubt you can ask me. Any doubt you can ask me. Everybody is okay with that? Now suppose it is fed from both the ends. It is fed from both the ends. Okay. So what you do in order to find the location of minimum voltage, Now, if you know the voltage drop in this case, can you tell me what is the location of minimum voltage and what is the value? Obviously, the location of minimum voltage is going to be the far end if it is fed from one side, and this very easily you can find if you know the total voltage drop, yes or no? It is going to be V, suppose it is V, so V minus total voltage drop is going to be the value of minimum voltage. But suppose it is fed from both the ends. If it is fed from both the ends, you break it into two pieces like a Kit Kat chocolate. Both the terminals are going to have V minimum. You write V minimum for both the sections and equate it, then you will be getting the expression. The expression for X you will be getting as V1 minus V2 upon L I R plus L by 2. I am not going to the derivation part because we don't have enough time. Now, what is this X? This X gives you location of V minimum, okay, from V1. Location of V minimum from V1. Let us do this question. There is a 250 meter distributor fed from both the ends, has a uniform current loading of 2 ampere per current, 2 ampere per meter. Find the location of minimum voltage and its value. So, can you find it? What is the location of minimum voltage? How you find the location of minimum voltage? This X is given as V1 minus V2 upon L I R plus L by 2. Now, what is V1 minus V2? It is 225, it is 220. So, this is 5 volts divided by L. What is L? L is given as 250 meters. What is I? I is 2 ampere per meter. What is R? R is given as loop resistance. So, no need to multiply by 2 because already loop resistance is given. Whenever loop resistance itself is given, you will not multiply it by 2. But if simply the conductor resistance is given, you understand it is the forward path and it is a return path. So, always you will use the loop resistance. Then you will multiply by 2. So, it is 0.2. Okay, ohms per kilometer. So, you have to divide it by 1000, multiply by 1000 here because it is kilometer, you have to change to meter, plus L by 2. What is L? 250. So, it is 125. To solve this, I think you must be getting it 175. 175 meters you must be getting. If you get the value of X, okay, suppose you are getting somewhere here, the location of minimum voltage. You got the value of X. It is 175 meters. Can you tell me what is the value of V minimum? Yes. Simply find the voltage drop for 175 meter. What is going to be voltage drop for 175 meter? Yes or no? It is going to be I into R into X square by 2. So, for 175 meters, it is going to be, what is I? 2. What is R? 0.2 divided by 1000 because kilometer has to be changed to meters. And L square by 2. What is L? 175. 175 square by 2. This is total voltage drop till here. So, what is V minimum? V minimum will become 225 minus delta V for 175 meters. You will be getting the value of minimum voltage. Is it clear, everybody? See, the best part of the class is only one student is doing the calculations. So, there is no problem. I am not worried about it because I know that rank 1 can only be one person. It cannot be 2 people. Okay. Anyways. So, you are getting it 218.875. Okay, whatever you are getting. I hope you understand the logic. Now, let me do one problem for the AC distributor. I think it should be ohm, okay? It is not W. It should be ohm. Okay. Now, only thing you have to remember when you are dealing with the AC distributor is that whenever the currents are mentioned, it's not just the magnitude, but you will be getting the power factor also. It means you will be getting that how much amount in terms of angle the current is lagging or leading. When it says 80 ampere 0.9 lag, it means this current is lagging the voltage of this terminal by cos inverse 0.9. That is the only thing you have to understand here while writing the expressions. So very easily you can solve it. Let me add some page here, then I will solve it. Okay. So what is the procedure? Just understand. He is asking what is the phase angle of Vs. He is asking what is the phase angle of Vs. Let us understand. Suppose this is node A, this is node B. The load connected to node B is IB, that is 120 ampere 0.8 lag. The load connected to node A is 80 ampere 0.9 lag. This is Z1, Z2, that is the impedances of these two sections, which is same 0.05 plus J 0.1 J ohms. The current here is IB. Okay, the current here is IB. Suppose the current taken by this load is, sorry, IA. Okay, this is IB. So in this section the current is IB. This is IA. So the total current IS is going to be IA plus IB. If I know the current IS, if I know the current IB, if I know the voltage VB, can I find Vs very easily? Just write the KVL equation. Yes or no? Now voltage VB is given. Magnitude is given. Let us take it as a reference. So angle we are taking as 0. Now if this is VB, if VB you are assuming as the reference 230 angle 0 degree, can you tell me what is IB? Because IB he is magnitude giving 120 ampere. Power factor is 0.8 lag. So IB you can write as magnitude is 120 minus of cos inverse 0.8, because cos phi is given as 0.8. So phi is cos inverse 0.8. You can write it minus because it is lagging. Minus because it is lagging. So can you tell me what is this value? It is 120 angle minus 36.86 degrees. You have current IB, you have voltage VB. Can you tell me what is the voltage for A node, that is VA? Now VA is going to be VB minus IB and Z2. What is VB? It is 230 angle 0 degree minus what is IB? 120 angle minus 36.86 and Z2 is 0.05 plus J 0.1. Just solve this and you will be getting VB. Okay, so I hope you understand why they are not asking AC distributor in general, why they are asking all the time DC distributor, because the calculation is little lengthy given the time of the examination. Okay, so you can solve this A voltage. If you know the A voltage, can you tell me what is IA? Yes or no? IA magnitude is given, that is 80 ampere. Now what is the phase angle? Now this is very critical, very important. Can anybody just solve this for me? I don't have the reference for this. Can anybody solve this? Do you have the speed to calculate it fast? Okay. Waiting for your response. Okay, Raghuram, I think already solved. So it is 218. Everybody please confirm it once. Angle is minus 1.577. Minus 1.577 volts. Now understand this. You have to draw the phasor diagram. This is your VB. VB you have taken as the reference. So this is VB. IB is lagging this. IB is lagging this voltage by some angle, 36.86. You have found VA as magnitude 218 angle 1.577 something. So your VA is going to be something like this. This is VA. Okay. Now you have to write IA 80 magnitude, but this cos inverse 0.9. What is cos inverse 0.9? Just tell me. What is cos inverse 0.9? Can you tell me the value? Cos inverse 0.9. What is the value? What is the cos inverse 0.9? You forget about IB. We are not interested in IB, so just remove it. Okay, just remove it. So your IA current 80 is the magnitude. Now this is given as cos inverse 0.9. And what is this angle? This angle is 1.577. So when you are writing IA, you have to write minus of this total angle. This total angle you have to write. This is the concept here. This phi is going to be cos inverse 0.9 plus 1.577. Are you getting this? So cos inverse 0.9, you are getting 25.84. So if it is 25.84, this is 1.5777 degrees. You just add it up. How much you are getting? You want me to calculate? Let's check my calculation. 27.41 something. This is how you have to write IA. So once you get IA, now you can write what is IS. IS is IA plus IB. If you have IS, can you write VS? Yes. What is VS? VS is going to be, from this VA you can write VA minus IS Z1. You know what is VA, you know what is IS, you know what is Z1. Put the values, you can get. Are you getting this? Everybody just tell me in the comment section. Are you able to follow this? Correct है जी? मजा आ रहा है जी? Okay. So now we are going to start the power system stability. So till now the topics we have discussed, they are quite theoretical in nature. So that is why I have to discuss a lot of theory. Okay. If you talk about the stability, stability is basically defined as the capability of the system to get itself restored. Yes, calculation is lengthy for AC distributor, and that is the reason in GATE examination, generally when they are asking the question from distribution, they are asking the question from DC distributor. Okay. So number of times I have explained. Once again, let me tell you what is stability. Suppose I am standing like this, and there is a notorious student in my class, and he is coming from this side, and he is going to give me a push. Suppose he is pushing me like this, and I am able to lean down and get back like this. So if I can manage myself to get myself restored to a new equilibrium position, then I am going to be stable. Okay? This is how you can understand the stability. Why I have given you this example? Because without disturbance, there is no meaning of stability. So disturbance is going to be the criteria to define which type of stability you are dealing with. So you can understand power system stability, you can define in three ways. That is the steady state stability, transient stability, and dynamic stability. Steady state stability we are defining as the disturbances related to this type of stability is small and gradual changes, or disturbances is small and gradual changes. Now when you talk about transient stability, it is about sudden and large changes. Sudden and large changes. Dynamic stability deals with the disturbances which are small but continuous. Take the example of aircraft or car. How much luxury aircraft you are going to sit, the moment that aircraft is going to take off and when it is in the air and finally get landed, throughout this duration there will be a constant disturbance which cannot be avoided. It is because of the very nature or existence of the system. For God's sake, you don't have dynamic stability in your syllabus, so you need to focus on steady state stability and transient stability. Let us talk about the basic idea of stability, that in a stable system, for a certain change in the input, the output you have disturbance, the oscillations are going to be decreasing with respect to time. Then only you say that your system is going to be stable. For a given change or disturbance in the input, the oscillations at the output, they are damping out. Their magnitude is reducing in a small time, and finally they are getting a new stable value. For the unstable system, you can see for a certain change or disturbance in the input, the oscillations at the output, they are increasing. They are having increasing magnitude, and that is the reason the system becomes unstable. So how we are defining the steady state stability? Is small and gradual changes. The ability of the system to get itself restored to a new operating point given a disturbance which is small and gradual. Let us take the example of a single machine infinite bus system. XD is the direct axis synchronous reactance of the synchronous alternator, and suppose this X, what is this XG? Forget about this XG, okay, that XG is nothing. This is simply XL. So XL is going to be the reactance of the transmission line, you can understand. So whenever you want to write, suppose you are writing the approximate power angle equation, you are writing what is the real power received. This is the real and reactive power received at the receiving end. So if you want to write the real power received at the receiving end, it is going to be magnitude E, magnitude V. This should be magnitude V, okay? Typo mistake. Typo, you understand? Okay. V angle 0. So E magnitude V magnitude divided by total series reactance between the alternator and the infinite bus, single machine infinite bus system. So this is X equivalent, okay? And you have sin del. What is this X equivalent? This X equivalent is simply XD plus XL. This is the most simplest case you can imagine. Then you have, if you plot this is approximate power angle curve, okay, you must have revised it. So it is purely sinusoidal. At del is equal to 90, you are getting the P max. This P max is also defined as the steady state stability limit. What is the steady state stability limit? This is the maximum power which can be transferred over the line without losing the system stability. Okay. So 0 to 90 degree del angle, the slope of the curve is positive. So this is a stable region. Now del 90 to 180 degree, the slope of the curve is negative. So this is unstable region. And del 90 is like India-Pakistan border. This side is stable, this side unstable. Now you will be asking me, sir, why you are deciding by this dp by d del positive or negative? How the slope of the curve is deciding whether it is stable or not? So let me give you some idea. Okay. what happens? You understand by this. This is del, this is P. This is your power angle curve, approximate power angle curve. Now, at any point of time, the power which is demanded, the load which is connected is supposed like this. This is the power demanded, and this is P max sin del. Now, this P max sin del is the electromagnetic power which is generated. This is the power being generated by the generator. So, generator is going to follow this curve. But what is the demand? The demand is PM. The demand is PM. Okay. Now, understand one thing. You are saying, sir, suppose I want to increase the demand. Suppose I want to increase the demand. If you want to increase the demand, it means the generation also has to be increased. Yes or no? Suppose at this point, when it was PM, the concerned del angle was del naught, and at del naught, the generator was generating this much and it is being delivered. So there is a mismatch, equilibrium, everything is okay. Now you are saying, no, sir, I want PM plus delta PM. I want to increase the load demand. If you want to increase the load demand, then definitely del has to increase. Then only this much amount of power can be delivered. Yes or no? Now, if you are increasing the power demand, in the load frequency control of the alternator, up command is given. Up command is given. So, steam valve opened more. It means more steam coming. More steam coming means speed increasing. Speed increasing means what? It can only happen because of acceleration. It means del increasing. Very, very important. And the reverse is also true. If you reduce PM, there is a down command given, steam valve opening is reduced, okay, is closed a little more, less steam, speed reduces, deceleration, del reduces. It means your system is going to remain stable if whenever the load demand is increased, P has to be increased, and it is only possible when del is increasing. So it means if the change in P is positive, if the change in P is positive, then change in del has to be positive. It means dP by d del has to be positive. If change in P is negative, then change in del has to be negative. Once again, dP by d del is positive. And this is what we get is a stable system. Is it clear, everybody? I hope you are getting this. Everybody just tell me in the comment section, are you able to follow this or not? Hello, mister, how do you do? Are you getting what I am telling? So this is for the single machine infinite bus system. Now suppose you have two machine system. Two machine system, suppose this is E angle 0 and this is V angle minus del. Now why I have taken V angle minus del? Because it's not about whether E is having the angle or V is having the angle. It's about the relative phase angle. It's about the relative phase angle. Again, can you directly write? This is the reactance diagram for this. Okay. This is the reactance diagram for this. So how I am writing the real power received at the load side. This is the generator, this is a motor. So real power received I am going to write as magnitude E, magnitude V divided by total X equivalent. This is XL and this is XM also. So this time X equivalent, this is XD, this is XM, this is XL. So this time X equivalent becomes XD, XL plus XM. Okay. And sign of relative phase angle. Relative phase angle means what? This angle minus this angle. So 0 degree minus of minus del becomes sin del. This is how directly you can write even for a two machine system what is the real power transferred. And now you can write, now you can draw the approximate power angle curve and you can understand the stability. For steady state stability, how you are defining the X equivalent, it is the total series reactance between the generator and the infinite bus. Or two machines operating together. What is del? Understand, very, very important in solving problems in the GATE examination. Del is the relative displacement angle between the voltage at the two terminals. Suppose you are having like this V1, V2, X equivalent. Then let me tell you, let me give you some idea. If this is the case, can you tell me what is the real power received here? Can you tell me what is the real power received here? The real power received is going to be mod V1, mod V2, total series reactance equivalent. And what is the relative displacement angle? It is del 1 minus del 2. So it is sine of del 1 minus del 2. Is it clear? And we always deal with the stability in terms of real power, not with the reactive power. How we are defining the steady state stability limit? This is nothing but P max. It is nothing but P max. So it is the maximum real power which can be transferred without losing the system stability in terms of steady state stability. Then we have synchronizing power coefficient or rigidity factor. Synchronizing power coefficient or rigidity factor, very, very important for 2023 examination. I give it 7 stars, twinkle, twinkle, little star. How I wonder what you are, because there is a high possibility you will get a question. Now understand one thing. How we are defining the synchronizing power coefficient. dP d del at del naught is the synchronizing power coefficient. How we are defining the synchronizing power, that is also important. How we are defining the synchronizing power? So, if you have P is equal to P max sin del, where P max is mod V1 mod V2 upon X equivalent. Then you can say the synchronizing power coefficient dP by d del at del naught is going to be P max cos del naught. But the question arises, we are saying for a stable system, the synchronizing power coefficient should be as high as possible. Should be as high as possible. Okay. Why it is so? Now understand from this diagram. Suppose the demand is changed from PD to PD dash. Okay, PD to PD dash. It means the operating point has to go from, suppose this is A and this is B. From A to B, the operating point has to be changed. Initially it was del naught, now it is del 1. Now if the slope is high, then for a given change in the real power demand, the change in the del is going to be less. Yes or no? You understand by this? Understand by this. This is one slope. Okay, and suppose this is another slope. It is having more slope. So for a given change in real power, the change in del is going to be less, and for a stable system, the change in del has to be minimum. Yes or no? For a given change in P, you can understand. For a given change in the real power demand, the change in del has to be minimum. So more and more slope means more and more higher value for synchronizing power coefficient means more and more stable system. Just do this question. Now before you do this question, I want to tell you something. Then we will discuss this question. Very interesting, very good question. You remember that scene? I don't remember the name of the movie. When he says, you are a good question. I think it was Tanu Waits Manu. The second part. Yes or no? I am going to write the actual power angle equation. So you suppose this is a generator, this is a transmission line A, B, C, D, and this is the infinite bus. This is E angle del and this is V angle 0 degree. Now you have to write what is the real power received. The real power received you will be writing as mod E mod V, or let me write, okay, it's okay, let it be. Mod E upon mod V, this is mod B, this is cos of beta minus del minus mod A upon mod B mod V square cos of beta minus alpha. Now for P max here, for P max, the second term, everything is constant, beta constant, alpha constant, V constant, A constant, B constant. Only the first term can be varied. First term only del can be varied. So the maximum value of this is going to be when, for real power, when you have the maximum value for this factor. The maximum value for this factor is going to be when you have cos beta minus del as 1. So P max becomes mod E, mod V, mod B minus mod A, mod B, mod V square cos of beta minus alpha. And what is the condition? The condition is, yes, you are right. The condition for P max is that cos beta minus del has to be 1. It is possible when beta minus del is 0 or del is equal to beta. So if you draw the power angle curve, for this actual power angle equation, it is going to be something like this. So P max you are getting at del is equal to beta. Okay. This is P max or steady state stability limit. This is the stable region. This is the unstable region. Here the slope of the curve is negative. Here the slope of the curve is positive. Here the slope of the curve is 0. So this is marginally stable. Marginally stable. Is it clear, everybody? Okay. Now suppose we take the case of a short transmission line. For the short transmission line, what are the ABCD parameters? It is going to be 1Z01. So A becomes, magnitude becomes 1, alpha becomes 0 degree. Okay. Magnitude B becomes magnitude Z, that is under root R square plus X square. What is beta? It is tan inverse X by R. Okay, so these are the inputs you have to write in that equation. So now the real power received, if you write for a short transmission line approximation, it becomes mod E, mod V. Mod V is mod Z, and you are writing P max. You are writing P max. So cos beta minus del has to be 1 because del is equal to beta, minus mod A is 1, mod V is again mod Z. This is V square cos of beta minus alpha. Listen very carefully. Cos of beta. This beta is theta. Alpha is 0, so it is cos theta. What is cos theta? Cos theta you can write as, and suppose we are assuming that E and V magnitude are approximately same, because in per unit system almost these are the similar values. So E and V you can take approximately as the same magnitude. So it becomes mod V square. It is mod V square upon mod Z minus this is mod V square upon mod Z, and this cos theta means, if you write the impedance triangle, this is R, this is X, this is theta, this is Z. So what is cos theta? R by Z. It is R by Z. Now at the design level, I want to know what is the condition for which I can get the maximum of this maximum value. Okay, suddenly from the operating, we are going to the designing part, operation part to the designing part. So if you take the differentiation with respect to X, because Z is R square plus X square under root, so you will get the condition as X by R as under root 3 as the condition, and the value of this maximum real power delivered is going to be V square upon 4R. This is the conclusion I wanted to discuss with all of you. Now you can do this problem. He is saying an alternator magnitude is 1 per unit, XS is 0.2, is connected to an infinite bus. V magnitude is 1 per unit through a short transmission line of impedance Z, this. An external element, whenever you get this statement in the question, an external element is connected in series with the line to get a real power injection of 2.5. So first you check what is this. If it is maximum value of the P max, then you can apply the condition. What is maximum value of the P max? It is V square upon 4R. What is V? It is 1. So 1, 4. What is R? 0.1. So it is 2.5. It means he is talking about that condition. So directly you can write X by R is equal to root 3. Now what is this total X? Total X is going to be XS plus 0.2. So it is, what is XS? 0.2 plus 0.2. So this is 0.4 plus some external element is connected. So this is x external. This is r. R is given as 0.1. This is the root 3. Find what is this x external. You must be getting it minus 0.2267. Why you are getting this as minus? Because it should be capacitive in nature. Minus sign only tells you that the nature should be capacitive instead of inductive. Is it clear, everybody? So how easy this question becomes once you know the concept. Are you getting that? Yes. So I think we should stop here because I think it's enough time for you. 4 hours completed, more than 4 hours. Let us plan one more session where I can discuss. Yes. This type of questions are more probable to come in the examination, because if you do know the trick, if you know the method, if you know the concept, then you can do it. Otherwise also you can solve it, but it will take more time. Okay, that is the reason. Is it clear, everybody? So just tell me. I think we should stop here and let us plan one more session, because it's not going to be completed if I extend it up to 1 hour also. So let us plan a fresh class. So I have to discuss the complete protection is remaining, fault is remaining, and I have to discuss this dynamic stability also, economic load dispatch also. A lot of topics are there. So let us plan one session. It is going to be planned around, I think, maybe the end weekend we are going to plan it, and it is going to be a big session. Okay, because we cannot skip the content. Okay, we cannot skip the content, because what is the agenda for these sessions? The agenda for these sessions means that we are going to give you the complete revision. Okay, within 12 days complete revision. So thank you so much, friends. But before you leave, okay, before you leave, a lot of things I prepare to discuss with you, but it is not possible for you to sit for more than 4 hours. I can understand. So better plan one more class. You can understand it's a big subject. So thank you so much, friends, for joining me live in the discussion. Take care of yourself. And if you have not downloaded the BYJU'S exam prep, just scan this code. Yes, you will be getting the PDF right. No, you will be getting the PDF, don't worry. You will be getting the PDF right after the class. Yesterday, actually, I missed it. I was not having good health, that is why it was delayed. So thank you so much, friends. It was a nice time talking to you. Let us see you in the next session, and stay connected. Tomorrow I think we will be having the machines marathon. So stay connected and be ready for machines. Thank you so much. Take care. Thank you. Best wishes. Thank you.